Imagine a catastrophe so massive that it unfolds over hundreds of millions of years. An event so colossal that it involves trillions of stars, quadrillions of planets, and an amount of dark matter exceeding the mass of all visible matter in millions of galaxies. This is not the plot of a science fiction film, nor an abstract mathematical model. This is a real event happening right now in the depths of space, more than 5 billion light-years from Earth. This is MACS J0717, one of the most violent and energetic cosmic collision zones ever discovered by human telescopes, a place where the fundamental laws of physics manifest themselves in their most extreme and spectacular forms. When we look up at the night sky, we see a picture of apparent tranquility. Stars twinkle peacefully, constellations maintain their familiar patterns, and the moon follows its predictable path across the heavens. This celestial serenity has inspired poets, guided navigators, and comforted humanity for millennia. But this peaceful appearance is profoundly misleading. The universe is not a static museum where celestial objects hang motionless in the cosmic void. Instead, it is a dynamic arena of constant motion, violent collisions, and transformations that dwarf anything we experience on Earth. The forces at work in the cosmos operate on scales that challenge human comprehension, and nowhere is this more evident than in MACS J0717, a cosmic crossroads where four massive galaxy clusters are colliding simultaneously in a gravitational ballet of unimaginable violence and beauty. To understand what makes MACS J0717 so extraordinary, we must first understand what galaxy clusters are and why their collisions represent some of the most energetic events in the universe since the Big Bang itself. A galaxy cluster is not simply a collection of galaxies floating near each other in space. It is a gravitationally bound system, the largest structures in the universe held together by their own gravity. These cosmic cities contain hundreds or even thousands of individual galaxies, each galaxy itself containing billions or trillions of stars. Between these galaxies flows an ocean of superheated gas, plasma so hot that it glows with X-ray radiation, with temperatures reaching tens of millions of degrees. This intergalactic medium, as astronomers call it, contains more mass than all the stars in all the galaxies combined, though it remains invisible to optical telescopes because it emits its light in wavelengths our eyes cannot detect. But even this vast amount of visible and X-ray emitting matter represents only a small fraction of the total mass of a galaxy cluster. The dominant component, comprising approximately 85% of all the matter in these systems, is something we cannot see directly at all. This is dark matter, the mysterious substance that pervades the universe, revealing its presence only through its gravitational effects on light and visible matter. Dark matter does not emit light, does not absorb light, and does not interact with electromagnetic radiation in any way we can currently detect. It passes through ordinary matter as if it were a ghost passing through walls. Yet without dark matter, galaxy clusters would fly apart, their galaxies would disintegrate, and the universe as we know it could not exist. In MACS J0717, dark matter plays the role of an invisible choreographer, orchestrating a cosmic collision of unprecedented complexity and violence. The story of MACS J0717 begins, as all cosmic stories do, billions of years ago. The universe was younger then, approximately 8 billion years old compared to its current age of nearly 14 billion years. In the region of space that would eventually become MACS J0717, matter was beginning to accumulate. This was not a sudden process, but rather a gradual condensation that had been ongoing since shortly after the Big Bang. In the earliest moments of cosmic history, matter was distributed almost uniformly throughout space, with only tiny variations in density, fluctuations of about 1 part in 100,000. These minuscule irregularities were the seeds of all cosmic structure. Regions that were even slightly denser than average had slightly stronger gravity, which attracted more matter, which increased the gravity further, which attracted even more matter. This runaway process, known as gravitational instability, transformed the nearly uniform primordial universe into the cosmic web of structure we observe today. Over hundreds of millions of years, these overdense regions grew into the first stars, then the first galaxies, then groups of galaxies, and finally into the massive clusters we observe in the modern universe. But the process of structure formation did not stop with the creation of individual clusters. Galaxy clusters themselves continue to merge and combine, forming ever larger structures along the filaments of the cosmic web. The cosmic web is the large-scale structure of the universe, a vast network of filaments and sheets of matter separated by enormous voids. If you could zoom out and view the universe on the largest scales, you would see a pattern resembling a three-dimensional spider's web or the neural networks in a brain, with galaxy clusters located at the intersections where multiple filaments meet. MACS J0717 sits at exactly such an intersection, a cosmic crossroads where four separate streams of matter are flowing together simultaneously. This quadruple collision is extraordinarily rare. Most galaxy cluster mergers involve just two clusters, occasionally three. A four-way collision like MACS J0717 requires an exceptional cosmic coincidence, with multiple massive structures converging on the same point in space at the same time. The probability of such an event occurring is extremely low, which makes MACS J0717 one of the most unique cosmic laboratories we have ever discovered. To witness four massive galaxy clusters colliding simultaneously is to observe the universe in one of its most extreme configurations, a cosmic stress test that pushes matter, energy, and space-time itself to their limits. When astronomers first discovered MACS J0717 using ground-based telescopes in the early years of the 21st century, they immediately recognized that they were looking at something unusual. The cluster appeared extraordinarily massive and extended, with a highly irregular shape that suggested recent or ongoing dynamical activity. As observing technology improved and more powerful instruments were brought to bear on this cosmic collision zone, the true nature of MACS J0717 gradually revealed itself. The Hubble Space Telescope captured stunning optical images showing the distribution of galaxies, revealing elongated patterns and streams of galaxies stretching across millions of light-years. The Chandra X-ray Observatory detected the superheated gas being shocked and compressed by the collision, creating brilliant X-ray emissions that map out the violence of the encounter. Radio telescopes discovered vast regions of synchrotron radiation, produced by electrons accelerated to nearly the speed of light by shock waves propagating through the intergalactic medium. And gravitational lensing observations, which use the bending of light by gravity to map the distribution of dark matter, revealed the invisible scaffolding that dominates the mass of the system. The total mass of MACS J0717 is staggering beyond comprehension. Current estimates place it at approximately 3 quadrillion times the mass of our Sun, written in scientific notation as 3 times 10 to the 15th power solar masses. To put this in perspective, our entire Milky Way galaxy, with its estimated 200 to 400 billion stars, has a total mass including dark matter of perhaps 1 trillion solar masses. MACS J0717 is 3,000 times more massive than the Milky Way. If you could somehow gather all the matter within MACS J0717 and compress it into a single sphere, that sphere would have a diameter of approximately 15 million light-years, about 150 times the diameter of the Milky Way. This is mass on a scale that approaches the limits of what can exist as a single gravitationally bound structure in our universe. Only a handful of galaxy clusters known to astronomy rival or exceed the mass of MACS J0717, making it one of the most massive objects ever observed. But mass alone does not tell the full story of MACS J0717. What makes this system truly extraordinary is its dynamics, the violent motions and transformations occurring as 4 separate clusters merge into one. When galaxy clusters collide, the process is fundamentally different from collisions between solid objects like billiard balls or cars. Galaxy clusters are not solid. They are diffuse systems composed primarily of empty space. The distances between stars within galaxies are enormous compared to the sizes of the stars themselves. Our Sun, for example, is about 1 million miles in diameter, but the nearest star to our Sun is over 4 light-years away, approximately 25 trillion miles. On the scale of stars, the universe is almost entirely empty space. This means that when galaxies collide, the stars almost never actually hit each other. They pass through each other like two swarms of bees interpenetrating, with individual bees rarely colliding. However, while the stars pass through each other unscathed, other components of the colliding systems interact in far more violent ways. The hot gas that fills the space between galaxies does collide. When two clouds of intergalactic plasma moving at velocities of thousands of kilometers per second slam into each other, the result is a cosmic shock wave, a supersonic collision that heats the gas to temperatures exceeding 100 million degrees. At these temperatures, atoms are completely ionized, stripped of their electrons, and the plasma emits intense X-ray radiation. The energy released in these collisions is almost beyond imagination. A typical galaxy cluster merger releases approximately 10 to the 63rd power ergs of energy over the course of the collision, which takes place over hundreds of millions to billions of years. This is equivalent to the energy output of a trillion suns shining for millions of years, making galaxy cluster collisions the most energetic events in the universe since the Big Bang itself. In MACS J0717, we are not witnessing a simple two-body collision, but rather a four-way pileup where multiple streams of matter are converging from different directions simultaneously. Observational data reveals at least 4 distinct substructures within the system, each representing a separate galaxy cluster or massive group that is in the process of merging. These subclusters have masses ranging from a few hundred trillion to over a trillion solar masses each, and they are approaching each other at relative velocities of thousands of kilometers per second. When objects with such enormous masses collide at such high speeds, the results are spectacular and complex. The gas in each subcluster is being shock heated to extreme temperatures, creating multiple shock fronts that crisscross the system. The dark matter in each subcluster, which interacts only through gravity and not through electromagnetic forces, passes through the collision relatively unimpeded, creating an offset between the visible matter and the dark matter that provides crucial evidence about the nature of dark matter itself. One of the most fascinating aspects of MACS J0717 is what it tells us about dark matter through a phenomenon known as the bullet cluster effect, named after the first galaxy cluster where this phenomenon was clearly observed. In a collision between galaxy clusters, the different components separate from each other in characteristic ways. The galaxies, being made of stars that rarely collide, sail through the collision largely unaffected. The hot gas, which does collide and interact electromagnetically, is slowed down and heated by the collision, accumulating in the central region where the shock waves meet. But the dark matter, which interacts only gravitationally and not electromagnetically, passes through the collision without being slowed or heated, continuing onward with the galaxies. By mapping the distribution of each component using different observational techniques, optical telescopes for galaxies, X-ray telescopes for hot gas, and gravitational lensing for dark matter, astronomers can create three-dimensional maps showing how matter and dark matter behave during violent cosmic collisions. Gravitational lensing is the key technique that allows us to map the invisible dark matter in MACS J0717. This phenomenon, predicted by Einstein's general theory of relativity, occurs because mass curves spacetime, and light traveling through curved spacetime follows curved paths. When light from distant galaxies passes through or near a massive object like a galaxy cluster, the path of that light is bent by the cluster's gravity, causing the background galaxies to appear distorted, magnified, or multiply imaged. The amount of distortion depends on the total mass between us and the background galaxy, regardless of whether that mass is visible or dark. By carefully measuring the shapes and positions of thousands of background galaxies, astronomers can reconstruct the total mass distribution of the intervening cluster with remarkable precision. This technique has been applied to MACS J0717 using deep observations from the Hubble Space Telescope, creating detailed maps showing where the dark matter is located. These dark matter maps reveal a complex structure in MACS J0717, with multiple peaks corresponding to the 4 colliding subclusters, connected by bridges and filaments of dark matter. The dark matter peaks are generally coincident with the concentrations of galaxies, confirming that dark matter and galaxies move together during the collision, both being affected primarily by gravity. However, the peaks of dark matter are offset from the peaks in the X-ray emission from hot gas, showing that the gas has been slowed by the collision, while the dark matter has not. This is exactly the behavior predicted if dark matter is indeed a form of matter that interacts only gravitationally, providing some of the strongest evidence we have for the existence of dark matter and its properties. The collision occurring in MACS J0717 is not a single instantaneous event, but rather a process unfolding over an enormous span of time. Galaxy cluster mergers typically take hundreds of millions to over a billion years from first approach to final coalescence. The process can be divided into several phases, each with its own distinctive characteristics and physical phenomena. In the first phase, the approaching clusters are still separate systems, but their mutual gravity is beginning to affect each other. As they draw closer, they accelerate toward each other, converting gravitational potential energy into kinetic energy, the energy of motion. By the time the clusters actually collide, they may be moving toward each other at velocities of 2,000 to 3,000 km per second, comparable to 1% of the speed of light. At these velocities, relativistic effects become noticeable, though not yet dominant. The moment of first collision is called core passage, when the dense central regions of the two clusters interpenetrate. This is when the most dramatic phenomena occur. Shock waves form in the hot gas as supersonic flows collide, heating the gas to extreme temperatures and accelerating particles to relativistic speeds. These shock waves can extend for millions of light years, creating some of the largest coherent structures generated by astrophysical processes. Behind the shock fronts, the gas is compressed to densities far higher than typical for intergalactic space, and the increased density makes the gas radiate more intensely in X-rays. This is why merging galaxy clusters are among the brightest X-ray sources in the sky, sometimes outshining even the active supermassive black holes that power quasars. In MACS J0717, the situation is even more complex than a simple two-cluster merger because we have four clusters colliding, which means multiple shock fronts and multiple interaction regions. Observations suggest that the system is caught in a particularly dynamic state, with some subclusters still approaching for their first core passage while others have already passed through each other and are beginning to fall back together under their mutual gravity. This creates a chaotic environment where shock waves from different collisions may intersect, where gas is being compressed and heated from multiple directions simultaneously, and where the trajectories of the various components are highly complex and difficult to predict without sophisticated computer simulations. Computer simulations have become an indispensable tool for understanding systems like MACS J0717. Because galaxy cluster collisions take place over timescales of hundreds of millions of years, we cannot watch them unfold in real time. We see only a single snapshot, a freeze frame from a cosmic movie that has been playing for eons. To understand the full sequence of events, what came before and what will come after, astronomers use powerful supercomputers to simulate the collision process. These simulations begin with initial conditions representing the four separate clusters before collision, including realistic distributions of dark matter, galaxies, and hot gas. The simulations then evolve forward in time according to the laws of physics, calculating how gravity pulls the clusters together, how the gas flows and shocks, how galaxies move through the system, and how energy is transferred between different components. The computational challenge is enormous. A single high-resolution simulation of MACS J0717 might track billions of particles representing dark matter, millions of particles representing gas, and thousands of particles representing galaxies. The gravitational forces between all these particles must be calculated at each time step, along with the hydrodynamic forces affecting the gas. The simulations must run for billions of simulated years, with time steps small enough to accurately capture the rapid changes that occur during core passage. Even on the most powerful supercomputers available, such simulations can take weeks or months to complete. But the results are worth the effort. By comparing simulations to observations, astronomers can determine the likely history of the system, the masses and velocities of the colliding clusters, the current phase of the merger, and predictions for what the system will look like in the future. Simulations of MACS J0717 suggest that the system is in a relatively early phase of the merger process. The four subclusters have not yet fully coalesced into a single relaxed system. Instead, they are still distinct entities, though they are already gravitationally bound to each other and will inevitably merge over the next several 100 million years. The current configuration, with matter streaming in from multiple directions along cosmic web filaments, represents a transitional state between the separate clusters that existed in the past and the single massive cluster that will exist in the future. In perhaps 1 billion years, after multiple passages through each other, and the gradual dissipation of kinetic energy through gas shocks and dynamical friction, the subclusters will settle into a more symmetric, relaxed configuration, and MACS J0717 will appear as a typical massive galaxy cluster, with little visible evidence of its violent past. One of the most intriguing features of MACS J0717 is the presence of large-scale radio emission, revealing the existence of cosmic rays and magnetic fields pervading the intergalactic medium. Radio telescopes operating at frequencies of around 1 GHz have detected diffuse radio emission extending across the entire cluster, with a particularly bright region several million light-years across. This radio emission is produced by synchrotron radiation, which occurs when electrons moving at nearly the speed of light spiral around magnetic field lines. The characteristic spectrum and polarization of synchrotron radiation allow astronomers to determine both the strength of the magnetic field and the energy distribution of the relativistic electrons producing the emission. The presence of these relativistic electrons poses an interesting puzzle. Electrons accelerated to such high energies lose their energy rapidly by synchrotron radiation, with timescales of only millions to tens of millions of years. This is extremely short compared to the age of galaxy clusters, which are typically billions of years old. Therefore, the relativistic electrons we observe must have been accelerated relatively recently, on cosmic timescales. The question is, what accelerated them? The leading theory is that shock waves in the intergalactic medium act as cosmic particle accelerators. As shock waves propagate through the plasma, they can accelerate a small fraction of the particles to extremely high energies through a process called diffusive shock acceleration. This is the same mechanism believed to be responsible for cosmic rays throughout the universe, from supernova remnants in our own galaxy to the most powerful extragalactic sources. The shock waves in MACS J0717 are some of the most powerful in the known universe, with velocities exceeding 2,000 km per second in Mach numbers, the ratio of the shock velocity to the speed of sound in the medium, reaching values of 3 or higher. Under these extreme conditions, shock acceleration can produce electrons with energies of trillions of electron volts, making them truly relativistic. These electrons then radiate away their energy as they spiral around magnetic field lines, producing the radio emission we observe. The spatial correspondence between the radio emission and the shock fronts detected in X-rays provides strong evidence for this shock acceleration scenario. In some regions of MACS J0717, astronomers have even detected sharp edges in the radio emission that coincide with X-ray detected shock fronts, providing direct observational evidence for particle acceleration at these cosmic shock waves. The magnetic fields in galaxy clusters are another fascinating aspect of the physics at work in MACS J0717. These magnetic fields, typically a few microgauss in strength, about 1/1,000,000th the strength of Earth's magnetic field, pervade the entire intergalactic medium. They are probably generated and amplified by a combination of processes, including the stretching and twisting of field lines by turbulent gas motions, the injection of magnetized plasma by radio galaxies with active supermassive black holes, and various dynamo processes that convert kinetic energy into magnetic energy. During cluster mergers, these magnetic fields can be significantly amplified by compression in shock waves and by turbulent motions generated by the collision. Observations suggest that the magnetic field strength in MACS J0717 is indeed enhanced compared to typical relaxed clusters, consistent with recent amplification by the ongoing merger activity. The turbulence generated by galaxy cluster mergers is itself a phenomenon of great interest. When massive subclusters collide, the resulting gas flows are highly supersonic and chaotic, generating turbulence across a vast range of spatial scales, from millions of light-years down to parsecs or less. This turbulence cascades from large scales to small scales, transferring energy downward through the inertial range until it reaches scales small enough for microscopic viscosity to dissipate the energy as heat. The turbulent motions provide pressure support against gravity, contribute to the mixing of different gas phases, amplify magnetic fields, and accelerate particles. Recent observations using X-ray spectroscopy have begun to directly measure the turbulent velocities in the hot gas of galaxy clusters by detecting the Doppler broadening of emission lines. These measurements confirm that merging clusters like MACS J0717 have substantially higher turbulent velocities compared to relaxed systems, providing quantitative evidence for the violent internal motions generated by these cosmic collisions. Another remarkable feature of MACS J0717 is its role as a gravitational lens. Because of its enormous mass, MACS J0717 bends light from even more distant galaxies located behind it, creating multiple images of those background galaxies and magnifying their apparent brightness. This gravitational lensing effect is both a tool for studying MACS J0717 itself and a window into the early universe. Some of the background galaxies lensed by MACS J0717 are among the most distant ever observed, with light that has been traveling through space for over 12 billion years, showing us those galaxies as they appeared when the universe was only about 10% of its current age. The magnification provided by MACS J0717 allows astronomers to study these distant galaxies in far greater detail than would otherwise be possible, revealing information about the first generations of stars, the assembly of the first galaxies, and the cosmic conditions during the universe's youth. The lensing effect also creates spectacular visual features. In Hubble Space Telescope images of MACS J0717, dozens of strongly lensed background galaxies are visible, stretched into long arcs that curve around the cluster's gravitational potential. Some background galaxies appear multiple times, with their images scattered around the cluster in patterns that encode information about the mass distribution of the lens. The most dramatic examples are Einstein rings, nearly complete rings of light formed when a background galaxy is almost perfectly aligned with the cluster and our line of sight. These Einstein rings are direct visible confirmations of Einstein's predictions about gravity and spacetime, predictions made over a century ago and now routinely observed in nature. The study of MACS J0717 has also contributed to our understanding of the cosmic web, the large-scale structure of the universe. The cosmic web is the pattern formed by matter on the largest scales, with galaxy clusters located at the nodes of the web, connected by filaments of galaxies and dark matter that stretch across hundreds of millions of light years. Between the filaments are vast voids, regions of space with very little matter. MACS J0717 is located at an exceptionally rich node of the cosmic web, where four major filaments converge. Observations have detected streams of galaxies flowing along these filaments toward the cluster, direct evidence of the hierarchical assembly of structure in the universe. Some of these streams are visible in optical images as elongated concentrations of galaxies extending away from the main cluster. X-ray observations have also detected hot gas associated with these filaments, though the gas in filaments is generally much less dense and cooler than the gas within clusters themselves. The filaments feeding MACS J0717 are conduits for the transport of matter from the cosmic web into galaxy clusters. Simulations predict that approximately half of the baryonic matter in the universe resides not in galaxies or clusters, but in these filaments, forming a warm, hot intergalactic medium with temperatures of 100,000 to 10 million degrees. This warm, hot intergalactic medium has proven difficult to observe directly because it is too hot to emit significant optical or ultraviolet radiation but too cool to emit strongly in X-rays. Nevertheless, recent observations using both X-ray telescopes and ultraviolet absorption line spectroscopy have begun to detect this elusive medium in the filaments around MACS J0717, confirming theoretical predictions and helping to account for the missing baryons that have long puzzled cosmologists. The galaxies within MACS J0717 are themselves undergoing dramatic changes as a result of the cluster merger. When a galaxy falls into a galaxy cluster, it encounters an environment very different from the relative isolation it experienced in the field. The intergalactic medium within clusters is hot and dense, and as a galaxy moves through this medium, it experiences a pressure like a wind in its face, a ram pressure that can strip away the galaxy's own gas. Since star formation requires gas, removing a galaxy's gas reservoir shuts down future star formation, causing the galaxy to age and redden as its blue, massive stars die without being replaced. This process, called ram pressure stripping, is particularly effective in merging clusters where the subclusters are moving rapidly through the intergalactic medium. Observations of galaxies in MACS J0717 show clear evidence of ram pressure stripping, with some galaxies displaying tails of stripped gas trailing behind them like the wake of a boat moving through water. Beyond ram pressure stripping, galaxies and clusters can also undergo direct gravitational interactions. When two galaxies pass close to each other, their mutual gravity can distort their shapes, trigger bursts of star formation, and in extreme cases lead to mergers where two galaxies coalesce into one. While the stars within galaxies rarely collide, the gas clouds can collide and shock, compressing the gas and triggering the collapse of new molecular clouds that form stars. Some of the most spectacular starburst galaxies, where stars are forming at rates hundreds or thousands of times higher than in the Milky Way, are found in merging systems. In MACS J0717, the combination of galaxy-galaxy interactions and the harsh cluster environment creates a laboratory for studying how galaxies evolve in extreme conditions. The supermassive black holes at the centers of galaxies also play a role in the physics of galaxy clusters. Many giant elliptical galaxies at cluster centers host active galactic nuclei, powered by supermassive black holes accreting matter from their surroundings. As matter falls toward the black hole, it forms an accretion disk where gravitational potential energy is converted to heat, producing intense radiation across the electromagnetic spectrum. Some of this energy is channeled into powerful jets of relativistic plasma that shoot out perpendicular to the accretion disk, extending for hundreds of thousands or even millions of light years. These jets deposit enormous amounts of energy into the surrounding intergalactic medium, creating bubbles and cavities in the hot gas that can be detected in X-ray images. This feedback from active galactic nuclei is thought to be crucial for regulating star formation in massive galaxies and preventing the hot gas and cluster cores from cooling and forming stars too efficiently. In MACS J0717, several bright radio sources associated with active galactic nuclei have been detected, including extended radio jets and lobes. The interaction between these radio sources and the cluster merger is complex. On one hand, the merger-induced turbulence and gas motions can affect the morphology and evolution of the radio sources, bending or disrupting the jets. On the other hand, the relativistic electrons and magnetic fields injected into the intergalactic medium by the radio sources may contribute to the diffuse radio emission observed throughout the cluster. Understanding the interplay between active galactic nuclei and cluster mergers is an active area of research, with important implications for the evolution of both galaxies and clusters. The temperature structure of the hot gas in MACS J0717 is remarkably complex, as revealed by X-ray spectroscopy. Different regions of the cluster have different temperatures, reflecting the different physical processes at work. In the cores of the individual subclusters, before collision, the gas is relatively cool, perhaps 20 to 30 million degrees. In the shock-heated regions where gas has been compressed by the merger, temperatures can exceed 100 million degrees. In regions where cool gas from the filaments is flowing into the cluster, temperatures may be lower, perhaps only a few million degrees. By mapping the temperature distribution in detail, astronomers can identify shock fronts, cold fronts where cool gas is sloshing around in the cluster potential, and regions where different gas phases are mixing. Cold fronts are particularly interesting features found in many merging galaxy clusters. Despite their name, cold fronts are not truly cold. They mark sharp boundaries between gas at temperatures of tens of millions of degrees and gas at temperatures of perhaps 40 or 50 million degrees, a difference of only a factor of 2 or so. What makes cold fronts remarkable is that they are extremely sharp, with temperature changes occurring over distances of only a few tens of thousands of light years, tiny compared to the multi-million light-year scale of the cluster. According to standard physics, such sharp boundaries should be rapidly erased by thermal conduction, with heat flowing from the hotter region to the cooler region until the temperatures equalize. The fact that cold fronts remain sharp indicates that thermal conduction is somehow suppressed, probably by magnetic fields that are tangled and prevent heat from flowing across the boundary. Cold fronts thus provide valuable probes of the microphysical properties of the intergalactic medium, including the magnetic field structure and the nature of plasma instabilities. Several cold fronts have been identified in MACS J0717, associated with the cool cores of infalling subclusters. As these subclusters move through the hot gas of the main cluster, their cool cores are stripped away, leaving behind sharp edges that mark the boundaries of the cold fronts. The shapes of these cold fronts encode information about the motion of the subclusters, the viscosity of the intergalactic medium, and the strength and orientation of magnetic fields. In some cases, the cold fronts show Kelvin-Helmholtz instabilities, distinctive spiral or wave-like patterns along the edge that develop when two fluids with different velocities flow past each other. These instabilities are familiar from everyday experience. They are responsible for the patterns in clouds and the ripples that form when wind blows across water. Seeing similar patterns in the intergalactic medium, on scales of millions of light-years, demonstrates that the same fundamental physics operates across an enormous range of scales, from the terrestrial to the cosmic. The energy budget of MACS J0717 is staggering. The total gravitational potential energy of the system, the energy that would be released if all the matter in the cluster were to fall together from infinity, is approximately 10 to the 63rd power ergs, equivalent to the mass energy of about 10 million solar masses converted entirely to energy according to Einstein's equation E = mc squared. During the collision process, a fraction of this energy, perhaps 10%, is converted into kinetic energy of gas motions and then dissipated as heat and radiation. This energy injection heats the gas to extreme temperatures and accelerates particles to relativistic speeds, creating the spectacular phenomena we observe. To put this energy in perspective, it is equivalent to the total energy output of all the stars in a million galaxies like the Milky Way over their entire lifetimes. And this is occurring in a single cosmic collision. One might wonder what this collision looks like from the inside. Imagine you were an observer on a planet orbiting a star in a galaxy located in one of the subclusters falling into MACS J0717. What would you see? At first, very little would appear unusual. The collision happens so slowly by human standards that you would notice no changes from year to year, or even from century to century. Your sky would look much like our sky does, with stars in your galaxy forming familiar constellations. But if you were patient and watched for millions of years, using instruments to detect the subtle changes, you would begin to notice some remarkable things. The galaxies in the neighboring cluster, the one you are colliding with, would gradually grow larger in angular size and brighter as they approached. Eventually, they would appear not as distant fuzzy blobs but as distinct swarms of stars, filling larger and larger portions of your sky. As the collision progressed, you might notice X-rays from the shock-heated gas if you had the right detectors. The sky would begin to glow in X-rays as the collision heated the intergalactic medium to extreme temperatures. If your planet happened to be located near the shock front, you might even detect an increase in cosmic ray flux as relativistic particles accelerated by the shock passed through your region of space. These cosmic rays could potentially pose a hazard to life if the flux was high enough, though whether it would be lethal depends on many factors. The gravitational effects would also become noticeable. The tides raised by the approaching cluster would begin to disturb the orbits of objects in your galaxy. Some stars might be pulled away, joining the intergalactic medium between clusters. Your galaxy itself might be stretched and distorted by the differential gravitational pull. Eventually, your galaxy would pass through the core of the opposite cluster. During this core passage, the density of the intergalactic medium would increase dramatically, and ram pressure stripping would become severe. If your galaxy contained significant amounts of gas, much of it would be stripped away, leaving bright trails of glowing gas behind. Star formation in your galaxy would cease as the gas reservoir was depleted. The sky would become filled with galaxies, so many that they would be visible everywhere you looked, no longer rare and distant but common and close. Your galaxy would be just one among thousands, all swirling around each other in a gravitational dance. And yet, despite all these dramatic changes, individual stars would still rarely collide. The spaces between stars are so vast that even when galaxies merge, stellar collisions remain extraordinarily improbable. Your star and planet would likely survive the encounter, though they might end up in a different part of the merged cluster, perhaps ejected to a remote region far from the center. From a cosmological perspective, MACS J0717 represents an important phase in the evolution of the universe. In the early universe, shortly after the Big Bang, structure was just beginning to form. Small fluctuations in the density of matter began to collapse under their own gravity, forming the first dark matter halos, then the first stars and galaxies. Over billions of years, these structures merged and combined, building up the cosmic web we observe today. Galaxy clusters represent the largest gravitationally bound systems that have had time to form in the age of the universe. They are the endpoints of hierarchical structure formation, the culmination of billions of years of gravity pulling matter together. But cluster formation is not complete. Clusters continue to merge with each other even today, though the merger rate was higher in the past when the universe was younger and denser. MACS J0717, with its redshift of 0.548, is seen as it was approximately 5.4 billion years ago, when the universe was about 8 billion years old, roughly 60% of its current age. At that epoch, the cosmic merger rate was higher than it is today, and massive collisions like the one occurring in MACS J0717 were more common. Today, in the local universe, most nearby galaxy clusters are relatively relaxed systems that have not experienced major mergers in the recent past. The fact that we observe MACS J0717 in such a dynamically active state is partly a selection effect. We tend to discover and study the most massive and luminous clusters, which are often those that are currently undergoing mergers, but it also reflects the fact that at earlier cosmic epochs, mergers were more frequent. By studying clusters at different redshifts, astronomers can trace the history of structure formation, observing how clusters have grown and evolved over cosmic time. The future of MACS J0717 is, in a sense, more predictable than its past. Given sufficient time, the collision will eventually end. The subclusters will merge completely, their gas will settle into a hot, quasi-static atmosphere in hydrostatic equilibrium with the gravitational potential, and the system will appear as a single massive relaxed cluster. The kinetic energy of the collision will have been dissipated as heat and radiation. The turbulence will decay. The shock waves will weaken and eventually disappear. The magnetic fields will evolve and possibly decay, though this process is poorly understood. The galaxies will settle into new orbits, and the cluster will gradually evolve toward a state of maximum entropy, where no further evolution is possible without external influence. This final state will be a massive, symmetric, nearly featureless cluster, with little to indicate its violent past except perhaps for some fossil evidence in the distribution of galaxies or in the properties of the hot gas. But this final state is still hundreds of millions to billions of years in the future. For now, MACS J0717 remains a spectacular example of cosmic violence, a laboratory for studying extreme physics, and a window into the fundamental processes that shape the universe. Every photon we receive from MACS J0717, whether in optical, X-ray, or radio wavelengths, carries information about the conditions in that distant cluster, information that astronomers painstakingly decode to reconstruct the story of the collision. Each observation adds another piece to the puzzle, helping us understand not just this particular system, but the general principles governing how matter behaves under extreme conditions, how structure forms in the universe, and how the cosmos has evolved from its simple beginnings to its current complex state. The study of MACS J0717 also highlights the power and importance of multi-wavelength astronomy. No single telescope or wavelength band can provide a complete picture of this complex system. Optical telescopes show us the galaxies, the fundamental building blocks, and through gravitational lensing reveal the distribution of dark matter. X-ray telescopes detect the hot gas, the shock fronts, and the energy dissipation. Radio telescopes trace the relativistic electrons and magnetic fields. Infrared telescopes can penetrate dust and reveal star formation. Ultraviolet telescopes probe the warm, hot intergalactic medium and the most massive stars. By combining observations across the electromagnetic spectrum, astronomers construct a comprehensive multidimensional picture of the collision, seeing it simultaneously in many different ways, each revealing different aspects of the physics at work. The techniques used to study MACS J0717 represent some of the most advanced observational and theoretical methods in modern astronomy. Gravitational lensing analysis requires measuring the shapes of thousands of faint background galaxies with exquisite precision, then inverting those measurements to reconstruct the mass distribution of the lens. X-ray spectroscopy requires detecting and analyzing individual photons from a source billions of light years away, determining their energies with precision sufficient to identify specific atomic transitions and measure Doppler shifts from gas motions. Radio interferometry combines signals from multiple telescopes separated by thousands of kilometers to synthesize images with resolution finer than any single telescope could achieve. Numerical simulations require solving the equations of gravity and hydrodynamics for billions of particles on supercomputers running for weeks or months. Each of these techniques pushes the boundaries of technology and methodology, driving innovation in detectors, telescopes, algorithms, and computational hardware. The discoveries made in systems like MACS J0717 also have implications far beyond cluster physics. The shocks in galaxy clusters are thought to be among the accelerators of ultra-high-energy cosmic rays, particles with energies exceeding 10 to the 20th electron volts, the most energetic particles ever observed in nature. The origin of these ultra-high-energy cosmic rays has been a mystery for decades. They possess too much energy to have been accelerated in ordinary supernovae, and they are so energetic that they can travel across intergalactic space without being deflected by magnetic fields, making it possible in principle to trace them back to their sources. However, they are also so energetic that they interact with the cosmic microwave background radiation, losing energy as they travel, which limits their range to a few 100 million light-years. Galaxy cluster merger shocks, with their enormous size and high velocities, are among the few astrophysical sites capable of accelerating particles to such extreme energies. If confirmed, this would establish yet another way that galaxy clusters shape the cosmos, not just through their gravity and gas, but by filling the universe with the highest energy particles known. The magnetic fields in galaxy clusters may also have cosmological significance. If clusters possess magnetic fields, those fields must have originated somewhere. One possibility is that seed magnetic fields were present in the early universe, generated by processes in the first moments after the Big Bang or during the epoch of first star formation. These seed fields would then be amplified by dynamo processes and turbulence as galaxies and clusters formed. Alternatively, magnetic fields could be generated later by astrophysical processes, such as the outflows from the first stars and galaxies, or by active galactic nuclei. By measuring the strength and structure of magnetic fields in clusters at different redshifts, astronomers can constrain the origin and evolution of cosmic magnetism, a question that touches on fundamental physics and the conditions of the early universe. MACS J0717 is also helping astronomers refine their understanding of dark matter. The standard model of cosmology, known as lambda CDM, assumes that dark matter is cold, meaning it was moving slowly when structure began to form, and that it interacts only gravitationally. This model has been remarkably successful at explaining the large-scale structure of the universe, the cosmic microwave background radiation, and the formation of galaxies and clusters. However, some observations on small scales have raised questions. For example, simulations predict that dark matter halos should have dense cusps at their centers, but observations of galaxies sometimes suggest flatter cores. Simulations also predict more small satellite galaxies around large galaxies than are actually observed. These discrepancies have led some physicists to propose that dark matter might have additional properties, such as self-interactions, where dark matter particles can scatter off each other even though they don't interact with ordinary matter. Galaxy cluster mergers provide a way to test for dark matter self-interactions. If dark matter particles can scatter off each other, then during a cluster collision, the dark matter in the two clusters would not pass through each other unimpeded, but would interact and be slowed down. This would cause the dark matter to lag behind the galaxies, whereas in the standard non-interacting cold dark matter model, the dark matter and galaxies should move together. By measuring the offset between the dark matter and the galaxies in merging clusters, astronomers can place limits on the dark matter self-interaction cross-section. Current observations of many systems, including MACS J0717, are consistent with dark matter having at most a very small self-interaction cross-section, supporting the standard cold dark matter model. However, more observations and better measurements are needed to definitively rule out all forms of self-interacting dark matter. Another profound question that MACS J0717 helps address is the nature of gravity itself. Einstein's general theory of relativity has passed every test to which it has been subjected, from the bending of starlight during solar eclipses to the precise timing of pulsar signals to the recent detection of gravitational waves from colliding black holes and neutron stars. However, general relativity has primarily been tested in relatively weak gravitational fields, such as those of the Sun, Earth, or stellar mass compact objects. Galaxy clusters provide an opportunity to test gravity in a very different regime, weak gravity but on enormous scales. Alternative theories of gravity, proposed to explain the acceleration of the universe's expansion without invoking dark energy, often make predictions that differ from general relativity on large scales. By carefully measuring the lensing signal and comparing it to the distribution of matter inferred from other observations, astronomers can test whether gravity behaves as general relativity predicts on scales of millions of light years. So far, observations including those of MACS J0717 support general relativity, but the tests continue to improve in precision. The question of dark energy, the mysterious component driving the accelerated expansion of the universe, also connects to observations of galaxy clusters. The abundance and properties of galaxy clusters are sensitive to cosmological parameters, including the amount of dark energy, the amount of dark matter, and the initial fluctuations in the density of the early universe. By surveying large numbers of galaxy clusters and measuring their masses and redshifts, astronomers can constrain these cosmological parameters. Massive clusters like MACS J0717 are particularly valuable because they are rare, and the exact number of very massive clusters that exist at different cosmic epochs depends sensitively on cosmology. Too few massive clusters would suggest more dark energy or smaller initial fluctuations, while too many would suggest less dark energy or larger fluctuations. Current cluster surveys are providing some of the tightest constraints on dark energy and are helping to determine whether dark energy is consistent with a simple cosmological constant, as Einstein proposed, or whether it evolves with time, which would point to more exotic physics. As we contemplate MACS J0717, we are also contemplating our own place in the universe. The Milky Way galaxy, our home, is part of a small group of galaxies called the Local Group, which includes the Andromeda Galaxy and about 50 smaller galaxies. In about 4 billion years, the Milky Way and Andromeda will collide and merge, creating a new elliptical galaxy that astronomers have informally named Milkomeda. This future collision will be similar in many ways to the galaxy-galaxy collisions occurring in MACS J0717 today, though on a smaller scale since only 2 galaxies are involved rather than thousands. The processes we observe in distant clusters, gravitational interactions, tidal stripping, shock heating of gas, triggered star formation, will eventually occur in our own cosmic neighborhood. Our Sun will likely survive the collision, though it may be flung into a different orbit, possibly far from the galactic center. The night sky as seen from Earth will be dramatically transformed, with Andromeda looming large and eventually merging with the Milky Way's stars, creating new patterns and new constellations. On an even larger scale, the Local Group is at the edge of the Virgo supercluster, a vast collection of galaxy groups and clusters stretching across 100 million light-years. At the heart of the Virgo supercluster is the Virgo cluster, a massive galaxy cluster containing over 1,000 galaxies. The Local Group is slowly falling toward the Virgo cluster under its gravitational pull, though we will not reach it for perhaps 20 billion years, long after the Sun has died. But we are also part of an even larger structure, the Laniakea supercluster, defined by the pattern of galaxy motions across 500 million light-years. All the galaxies in Laniakea are slowly flowing toward a region called the Great Attractor, a concentration of mass whose exact nature is still debated. These cosmic flows reveal that even the largest structures in the universe are not static but are in motion, merging and growing over time scales of billions of years. MACS J0717, located far from our own cosmic neighborhood, is undergoing a process that is ultimately similar to what the local group experiences: the gradual assembly of structure through gravitational attraction and mergers. The light we receive from MACS J0717 left that cluster 5.4 billion years ago, when the Earth itself was only about 200 million years old, just emerging from the most recent great bombardment of asteroids and comets. Life on Earth existed only in the form of single-celled organisms, and the first multicellular life would not evolve for another billion years. The light has been traveling through space for longer than complex life has existed on Earth, crossing an expanding universe, gradually losing energy as its wavelengths stretched due to cosmic expansion, until it finally reached Earth and entered our telescopes. In that time, the collision in MACS J0717 has progressed, perhaps entering a new phase, with the subclusters moving closer or beginning to fall back together. We cannot know the current state of MACS J0717 because we see it as it was in the past. The collision is still happening, but we are seeing it in an ancient light, a light that connects us across space and time to events of unimaginable scale and violence. This temporal distance highlights one of the profound aspects of astronomy. We study the universe not as it is, but as it was. The farther we look, the further back in time we see. The most distant objects visible to our telescopes are seen as they were more than 13 billion years ago, when the universe was in its infancy. This makes astronomy a form of time travel, a way to study cosmic history directly by observing light that has been journeying toward us for billions of years. Every astronomical observation is an archaeological excavation, uncovering the past layer by layer as we probe deeper into space. MACS J0717, at a look-back time of 5.4 billion years, is relatively nearby in cosmological terms, but it still shows us the universe at a time when it was younger, denser, and more violent than today. The technology required to observe MACS J0717 in such detail is itself a marvel of human ingenuity. The Hubble Space Telescope, launched in 1990 and still operational after more than 3 decades in orbit, has provided some of the deepest and most detailed images of the cluster. Hubble's position above Earth's atmosphere allows it to capture images with unprecedented clarity, free from the blurring effects of atmospheric turbulence. The Chandra X-ray Observatory, launched in 1999, has revealed the hot gas and shock fronts with exquisite sensitivity. Ground-based radio telescopes, including the Very Large Array in New Mexico and the Low Frequency Array in Europe, have mapped the diffuse radio emission and revealed the magnetic fields and relativistic electrons. Future telescopes will provide even more detailed views. The James Webb Space Telescope, launched in 2021, is observing the universe in infrared wavelengths with sensitivity far exceeding anything before, and it is being used to study galaxy clusters like MACS J0717 and the high redshift galaxies they magnify. The upcoming extremely large telescopes, with mirrors 30 to 40 meters in diameter, will provide optical and infrared observations with 10 times better resolution than current ground-based telescopes. Each generation of telescopes has revealed new phenomena and answered old questions while raising new ones. Early observations of galaxy clusters using optical telescopes in the 20th century showed that galaxies are not randomly distributed but are clustered, and that clusters contain thousands of galaxies. Later observations revealed that clusters emit X-rays, leading to the discovery of the hot intergalactic medium. Observations of galaxy velocities in clusters suggested the presence of far more mass than could be accounted for by visible matter, providing some of the first evidence for dark matter. Gravitational lensing observations confirmed that this dark matter exists and showed that it dominates the mass of clusters. Radio observations revealed magnetic fields and cosmic rays. Each new wavelength band, Each improvement in sensitivity and resolution has peeled back another layer of the cosmic onion, revealing deeper truths about how the universe works. As our understanding of MACS J0717 has grown, so too has our appreciation for the interconnectedness of cosmic phenomena. The collision occurring in this distant cluster is not an isolated event but is connected to the large-scale structure of the universe, to the properties of dark matter and dark energy, to the behavior of hot plasma and magnetic fields, to the acceleration of cosmic rays, to the evolution of galaxies, and even to the fundamental laws of physics. By studying this single system in detail, astronomers are simultaneously studying cosmology, plasma physics, particle physics, gravitational physics, and astrophysics. MACS J0717 is a microcosm of the universe, a place where many of the most important processes in nature are occurring simultaneously and can be observed and analyzed. The sheer violence of the collision in MACS J0717 is humbling. We live on a small planet orbiting an ordinary star in a quiet suburb of a typical spiral galaxy. Our environment is, by cosmic standards, extraordinarily calm and stable. The sun shines steadily, providing the energy that powers life. The planets orbit in predictable patterns. Even the most violent events on Earth, earthquakes, volcanic eruptions, hurricanes, are tiny disturbances compared to cosmic phenomena. A powerful earthquake releases energy of perhaps 10 to the 18th ergs, equivalent to a megaton nuclear weapon. A major volcanic eruption might release 10 to the 24th ergs. The impact that killed the dinosaurs 66 million years ago released about 10 to the 31st ergs. Even a supernova, the explosion of a star, releases about 10 to the 52nd ergs. But the collision in MACS J0717 involves energies of 10 to the 63rd ergs or more, 10 billion times the energy of a supernova, sustained over hundreds of millions of years. It is difficult to comprehend such scales, difficult to imagine forces that can accelerate trillions of solar masses to thousands of kilometers per second, difficult to grasp the sheer magnitude of the event. Yet despite this violence, or perhaps because of it, galaxy cluster mergers are creative as well as destructive. The energy injected into the intergalactic medium prevents it from cooling and forming stars too rapidly, regulating the rate at which gas is converted into stars and allowing galaxies to continue forming stars over billions of years rather than consuming all their gas in a brief burst. The mixing and processing of gas by shocks and turbulence enriches the intergalactic medium with heavy elements produced in stars, spreading the products of stellar nucleosynthesis throughout the cluster. The magnetic fields amplified by the merger may protect galaxies from cosmic rays that would otherwise ionize their gas and suppress star formation. The merger itself is a step in the ongoing process of structure formation, building up the massive clusters that will dominate the universe in the distant future. From chaos and violence emerges order and structure, a theme that recurs throughout cosmic history. In contemplating MACS J0717, we might also reflect on the nature of scientific inquiry itself. For most of human history, the heavens were seen as eternal and unchanging, the realm of the gods, beyond human understanding. The stars and planets followed their courses, and humans could only watch and wonder. But over the past few centuries, and especially in the past few decades, we have learned to decode the light reaching us from the cosmos, to translate photons into information, to reconstruct the physical conditions in distant regions of space and time. We have learned that the universe is not eternal and unchanging but dynamic and evolving, that stars are born and die, that galaxies collide and merge, that the universe itself is expanding and had a beginning. We have learned that we can understand the cosmos, that the same physical laws that operate on Earth also operate in the most distant reaches of space, that nature is comprehensible to the human mind. The study of MACS J0717 exemplifies this quest for understanding. Armed with telescopes and equations, with patience and ingenuity, astronomers have reconstructed the story of this cosmic collision from photons that have traveled for billions of years to reach us. They have measured the masses of invisible dark matter halos, mapped the distribution of gas too hot to see with human eyes, detected shock waves millions of light-years across, and traced the motions of galaxies as they fall toward their doom. They have compared their observations to simulations run on powerful computers, tested their understanding of physics in extreme conditions, and contributed to our knowledge of how the universe evolved from simplicity to complexity. This is science at its finest, taking observations of nature, applying reason and mathematics, testing hypotheses, refining theories, and gradually building up a coherent picture of reality that is both beautiful and true. As we look to the future, the study of MACS J0717 and similar systems will continue to advance. New telescopes will provide better data. More sophisticated simulations will provide better theoretical understanding. New questions will arise, and some old questions will be answered. We will learn more about dark matter and dark energy, about the origin of cosmic magnetism, about the acceleration of cosmic rays, about the formation and evolution of galaxies, and about the large-scale structure of the universe. Each discovery will deepen our appreciation for the cosmos and our place within it, revealing new wonders and new mysteries. But beyond the specific scientific results, the study of MACS J0717 also speaks to something more fundamental: the human desire to explore, to understand, to reach beyond our immediate surroundings and grasp the nature of the wider universe. We are a curious species, driven to ask questions about the world around us and to seek answers. From our earliest ancestors looking up at the night sky and wondering about the lights they saw, to modern astronomers analyzing data from space telescopes, this curiosity has been a defining characteristic of humanity. MACS J0717 is far beyond our reach. We will never travel there, never see it up close, never touch it. Yet we can study it, understand it, and make it part of our mental model of the universe. In doing so, we expand our horizons and connect ourselves to the cosmos in a profound way. The collision in MACS J0717 will eventually end, the system will relax, and the cluster will settle into a quiet old age. But new collisions are always beginning elsewhere in the universe as gravity pulls structures together. The process of cosmic evolution continues, building up structure, creating ever larger systems, moving toward a future that we can predict in broad outline but not in detail. Eventually, in the very distant future, the expansion of the universe will dilute matter to such low densities that no new structures can form. The stars will burn out, black holes will evaporate, and the universe will become a cold, dark, empty place. But that is trillions of years in the future, an almost incomprehensibly long time. For now, and for the foreseeable future, the universe remains a dynamic, energetic, fascinating place, full of wonders like MACS J0717 waiting to be discovered and understood. In the end, MACS J0717 is more than just a galaxy cluster. It is a window into the fundamental processes that shape the universe, a laboratory for testing our theories of physics, a monument to the power of gravity and the vastness of cosmic scales, and a reminder of our own small but significant place in the grand scheme of existence. Every photon from MACS J0717 is a messenger bringing news from a distant time and place, news of collisions and shock waves, of dark matter and hot gas, of galaxies merging and stars being born and dying. By studying these messengers, by decoding their information, we participate in a grand cosmic story that began with the Big Bang and continues to unfold today. We are, in a very real sense, the universe becoming aware of itself, matter organized in such a way that it can contemplate its own existence and origins. That is perhaps the greatest wonder of all, and it is a wonder that systems like MACS J0717 help us to appreciate and understand. The intricate dance of matter within MACS J0717 reveals patterns that challenge our fundamental understanding of how energy and information propagate through cosmic structures. When shock waves traverse the intergalactic medium at velocities exceeding 2,000 km per second, they do not merely heat the gas. They fundamentally restructure the plasma at microscopic scales. The electrons and ions in the pre-shock gas are in rough thermal equilibrium, moving at speeds determined by the temperature of the medium. As the shock passes, particles are suddenly compressed and accelerated, but this process does not affect all species equally. The lighter electrons respond more quickly to electromagnetic forces, while the heavier ions carry more momentum. This creates a temporary separation between electron and ion temperatures, with ions being preferentially heated by the shock. Over time, through a process called Coulomb collisions, the electrons and ions exchange energy until they reach a common temperature, but this equilibration takes time, and in the interim, the plasma exists in a fascinating state of thermal disequilibrium. This non-equilibrium state has profound implications for the radiation we observe. X-ray emission from hot plasma depends primarily on electron temperature, since it is the electrons that radiate most efficiently through processes like Bremsstrahlung and line emission. If the electrons are cooler than the ions immediately behind a shock front, the X-ray emission will be suppressed compared to what we would expect for a fully equilibrated plasma. By carefully analyzing the X-ray spectra from different regions of MACS J0717, astronomers can search for signatures of this electron-ion disequilibrium. Providing constraints on the timescales for Coulomb collisions and the physics of shock heating. Recent observations with advanced X-ray spectrometers have begun to detect these subtle effects, confirming theoretical predictions and opening a new window into plasma microphysics at cosmic scales. The magnetic field amplification during cluster mergers follows a complex cascade of processes that span an enormous range of scales. Initially, the large-scale motions of the colliding subclusters stretch and compress the existing magnetic field lines, amplifying them through simple geometric effects. But this compression alone cannot explain the field strengths observed. Additional amplification occurs through turbulent dynamo processes, where chaotic motions at intermediate scales tangle and twist field lines, converting kinetic energy into magnetic energy. At the smallest scales, plasma instabilities can generate magnetic fields from scratch in regions where none previously existed. One particularly important instability is the Weibel instability, which can generate strong magnetic fields in collisionless shocks where counterstreaming particle beams are present. These microscopic fields, though initially small in spatial extent, can be stretched and amplified by larger-scale motions, feeding energy upward through the cascade and contributing to the cluster-scale fields we observe. Understanding this magnetic field evolution is crucial for interpreting the radio observations of MACS J0717. The diffuse radio emission extends across several million light-years, suggesting that relativistic electrons and magnetic fields permeate the entire cluster volume. But how did these relativistic electrons get there? Shock acceleration can explain particles near the shock fronts, but the radio emission extends far beyond any identifiable shocks. One possibility is that the relativistic electrons are old, produced by shocks or active galactic nuclei in the past, and have since spread throughout the cluster through diffusion. But electrons lose energy rapidly through synchrotron radiation and inverse Compton scattering, so old electrons should have radiated away most of their energy by now. This suggests that some mechanism is continually reaccelerating electrons throughout the cluster volume, maintaining the population of relativistic particles. Turbulence is the leading candidate for this reacceleration. Turbulent motions can accelerate particles through both compression and through interactions with magnetic irregularities, processes analogous to Fermi acceleration but operating in a turbulent rather than shock environment. The spectrum of the radio emission provides clues about the acceleration and energy loss processes. If electrons are accelerated to a power law distribution of energies and then radiate without further acceleration, their synchrotron spectrum will steepen at high frequencies, with the steepening occurring at frequencies corresponding to electrons that have lost most of their energy. By measuring the radio spectrum across a wide range of frequencies, from tens of megahertz to tens of gigahertz, astronomers can constrain the age of the electron population and the strength of the magnetic field. In MACS J0717, the radio spectrum shows evidence for spectral steepening in some regions, suggesting ages of several hundred million years for the electron population, comparable to the dynamical timescale of the merger. This supports the idea that the electrons we observe today were accelerated during the current merger event, rather than being remnants from much earlier times. Polarization measurements add another dimension to radio observations. Synchrotron radiation is intrinsically polarized, with the electric field vector perpendicular to the magnetic field direction. By measuring the polarization of radio emission across the cluster, astronomers can map the magnetic field direction and determine whether the field is ordered or tangled. In MACS J0717, polarization observations reveal a complex magnetic field structure, with some regions showing ordered fields aligned with the elongation of the cluster, suggesting that compression during the merger has stretched and aligned field lines. Other regions show low polarization, indicating tangled fields, possibly associated with turbulent regions where the field structure is chaotic. The degree of polarization is also affected by Faraday rotation, where the plane of polarization rotates as the radio waves pass through magnetized plasma. By measuring the rotation as a function of wavelength, astronomers can determine the integrated magnetic field strength along the line of sight, providing complementary information to the synchrotron-based field strength estimates. Beyond the immediate physics of the collision, MACS J0717 serves as a gravitational telescope, magnifying distant background sources through strong lensing effects. Some of the most remarkable discoveries made possible by this natural telescope are observations of extremely distant galaxies from the epoch of reionization, the period roughly 1 billion years after the Big Bang, when the first galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that filled the universe. These distant galaxies are intrinsically faint and would be barely detectable even with the most powerful telescopes available. But when they happen to be located behind MACS J0717, their light is magnified by factors of 10, 20, or even more, making them bright enough to study in detail. This magnification allows astronomers to observe galaxies that are too faint to be detected anywhere else, pushing observations back toward the very first generations of galaxies. One particularly interesting strongly lensed object behind MACS J0717 is a galaxy observed as it was approximately 12.5 billion years ago, only about 1 billion years after the Big Bang. The magnification provided by the cluster allows detailed spectroscopy of this ancient galaxy, revealing the chemical composition of its gas, the rate at which it is forming stars, and the properties of its stellar population. Surprisingly, this galaxy shows evidence of already being enriched with heavy elements, including oxygen, carbon, and nitrogen, despite its extreme youth. This enrichment implies that previous generations of stars must have already formed, lived their lives, and exploded as supernovae, injecting heavy elements into the interstellar medium. The rapidity of this chemical evolution suggests that the first stars formed even earlier than this galaxy, perhaps only a few 100 million years after the Big Bang, and that star formation and chemical enrichment proceeded very rapidly in the early universe. The lensing magnification is not uniform across the image plane. It is strongest near the critical curves, imaginary lines in the lens plane where the magnification formally becomes infinite. Objects located exactly on a critical curve would be magnified to infinite brightness, though in practice this never quite happens because galaxies have finite size. Nevertheless, galaxies near critical curves can be magnified by factors of 50 or 100, providing extraordinary sensitivity to faint features. Astronomers have developed sophisticated techniques to map the magnification pattern across MACS J0717, creating magnification maps that show where the lensing effect is strongest. These maps are essential for interpreting observations of lensed galaxies, since the observed brightness must be corrected for magnification to determine the intrinsic properties of the source. The time delays between multiple images of the same lensed galaxy provide another powerful probe of cosmology and cluster physics. When a background galaxy is multiply-imaged by a gravitational lens, light from the galaxy travels along different paths to reach Earth, and these different paths have different lengths. Moreover, because gravity affects the flow of time, light traveling through different gravitational potentials experiences different time dilations. The combination of geometric path length differences and gravitational time dilation produces a time delay between the images, typically ranging from days to years depending on the system. If the background galaxy is variable, for example, if it contains an active galactic nucleus that brightens and fades, then the variability will appear in one image before the others, with the time delays determined by the mass distribution of the lens. By measuring these time delays and modeling the lens, astronomers can determine the Hubble constant, the expansion rate of the universe, providing an independent method to measure this fundamental cosmological parameter. While time delay measurements are most commonly done with strongly lensed quasars, where the variability is strong and easily detected, the principles apply to any multiply-image variable source. The chemical composition of the intergalactic medium in MACS J0717 records the history of stellar evolution and feedback in the cluster. Heavy elements like oxygen, silicon, and iron are produced inside stars through nuclear fusion and are expelled into space when stars die, either through stellar winds or through supernova explosions. Over billions of years, these heavy elements accumulate in the intergalactic medium, enriching it from its primordial composition of hydrogen and helium. By measuring the abundances of different elements in the hot gas using X-ray spectroscopy, astronomers can determine how much stellar processing has occurred and constrain models of galactic chemical evolution. The pattern of abundances provides clues about which types of stars and supernovae were responsible for the enrichment. For example, oxygen is produced primarily in massive stars that explode as core collapse supernovae, while iron is produced in both core collapse and type Ia supernovae. The ratio of oxygen to iron therefore constrains the relative contributions of these different stellar populations. Observations of MACS J0717 reveal that the intergalactic medium has been enriched to approximately one-third of solar metallicity, meaning it contains about one-third as much heavy element abundance relative to hydrogen as the Sun does. This substantial enrichment indicates that the gas has been processed through many generations of star formation. Interestingly, the metallicity is relatively uniform throughout the cluster, without strong gradients or variations between different regions. This uniformity suggests that the metals have been efficiently mixed throughout the cluster volume, probably by a combination of galactic winds, ram pressure stripping, and turbulent motions. The mixing timescales must be comparable to or shorter than the enrichment timescales, otherwise we would observe stronger variations in metallicity corresponding to localized injection of metals from individual galaxies. The distribution of heavy elements also provides clues about the history of mergers in the cluster. When a subcluster falls into the main cluster, it brings with it gas that has its own enrichment history, potentially with different metallicity than the gas already present in the main cluster. During the merger, the different gas masses mix, but mixing is not instantaneous. Recent simulations suggest that complete mixing may take several billion years, comparable to the age of clusters. If MACS J0717 has experienced multiple mergers over its history, as seems likely, then the gas may still retain some memory of these events in the form of subtle metallicity variations. Detecting these variations requires high-quality X-ray spectroscopy with sufficient spatial resolution to map abundances across the cluster, a challenging observational task that is becoming possible with the latest generation of X-ray observatories. The presence of cool cores in some of the infalling subclusters adds another layer of complexity to the physics of MACS J0717. A cool core is a region in the center of a galaxy cluster where the gas density is high and the cooling time is short. In relaxed clusters, the gas in the central few 100,000 light-years can have cooling times shorter than the age of the universe, meaning it should cool, condense, and form stars at very high rates. However, observations show that this cooling catastrophe does not occur in most clusters. Instead, active galactic nuclei in the central galaxies heat the gas through jets and bubbles, preventing it from cooling. This balance between cooling and heating is called AGN feedback and is one of the most important processes regulating star formation in massive galaxies and galaxy clusters. When a subcluster with a cool core falls into a larger cluster, the fate of the cool core depends on the details of the merger. If the core is dense and compact, it may survive for hundreds of millions of years, sloshing around in the potential well of the merged system. If it is more diffuse or if the merger is particularly violent, it may be disrupted, with the cool gas being stripped away and mixed into the hotter intracluster medium. Observations of MACS J0717 show evidence for both scenarios. Some subclusters appear to retain compact cool cores that are still identifiable in X-ray images as dense, relatively cool regions. Others show signs of disruption, with elongated streams of cooler gas being stripped away from the subcluster centers. These streams can extend for hundreds of thousands of light years, tracing the trajectory of the subcluster through the cluster and providing a visible record of the merger history. The stripped cool gas is not simply heated to the temperature of the surrounding medium. Instead, it creates a complex multi-phase structure where cool, dense gas is embedded in a hot, diffuse medium. These multi-phase systems are inherently unstable. The cool gas has higher density and therefore higher pressure than it would if it were in thermal equilibrium with the surrounding hot gas. This overpressure drives expansion of the cool gas, but as it expands, it does work on the surrounding medium and cools further. At the same time, thermal conduction from the hot gas heats the cool gas, trying to bring it into equilibrium. The balance between these processes determines whether the cool gas survives or is evaporated. Magnetic fields can strongly suppress thermal conduction, allowing cool clouds to survive far longer than they would in a purely hydrodynamic situation. The presence of long-lived cool gas structures in MACS J0717 therefore provides evidence for tangled magnetic fields that inhibit heat flow. Star formation in the galaxies of MACS J0717 is strongly affected by their environment in multiple ways. As already discussed, ram pressure stripping removes gas from galaxies as they move through the intracluster medium, shutting down star formation. But the details of this process are more subtle than simply removing all the gas. Ram pressure is stronger in the outer parts of a galaxy's gas disk, where the gravitational restoring force is weaker. This means that gas is stripped preferentially from the outside in, a process called outside-in quenching. As a result, star formation may continue in the inner regions of a galaxy even after the outer regions have been stripped. Observations of galaxies in MACS J0717 show evidence for this process, with some galaxies displaying star formation in their centers but not in their outskirts. Additionally, before the gas is completely removed, the compression caused by ram pressure can actually trigger star formation. As the galaxy plows through the intracluster medium, the pressure on the leading edge of the galaxy's gas disk increases, compressing the gas and causing it to collapse into new stars. This produces what is called a ram pressure-induced starburst, where the star formation rate temporarily increases before the gas is stripped away and star formation ceases entirely. Some galaxies and cluster environments show evidence of this process, with bright young stars and star-forming regions concentrated on one side of the galaxy, the side facing the direction of motion through the cluster. In MACS J0717, the high velocities and dense gas make ram pressure stripping particularly effective, and several galaxies show morphologies consistent with ongoing stripping and possible triggered star formation. Galaxy harassment is another environmental process that affects galaxies and clusters. This refers to the cumulative effect of multiple high-speed gravitational encounters between galaxies. Unlike a major merger where two galaxies of comparable mass coalesce, harassment involves many weaker interactions. Each individual encounter may not significantly affect the galaxy, but the cumulative effect of many encounters can heat the stellar disk, causing it to thicken and transform from a thin, rotationally supported disk into a thicker, pressure-supported system. Over time, harassment can transform disk galaxies into dwarf elliptical or irregular galaxies, changing the morphological mix of the cluster population. The effectiveness of harassment depends on the orbital velocities and the density of galaxies. In rich clusters like MACS J0717, where encounter velocities are high and galaxy number densities are also high, harassment can be an important evolutionary mechanism. Tidal interactions provide yet another way that the cluster environment affects galaxies. When a galaxy passes near another galaxy or through a strong gravitational gradient in the cluster potential, tidal forces stretch the galaxy along the radial direction and compress it in the tangential direction. These tidal forces can trigger instabilities in the galaxy's disk, driving bars, spiral arms, or even tidal tails of stars that are pulled out of the main galaxy. In extreme cases, tidal forces can completely disrupt a galaxy, spreading its stars throughout the cluster to form the intracluster light, a diffuse population of stars that are not bound to any individual galaxy but instead orbit in the cluster potential as a whole. Observations of MACS J0717 reveal significant amounts of intracluster light, suggesting that tidal disruption has been effective in transferring stars from galaxies to the cluster environment. This intracluster stellar population contains clues about which galaxies have been disrupted and when, providing another probe of the cluster's assembly history. The supermassive black holes at the centers of galaxies play a multifaceted role in cluster physics. As mentioned earlier, active galactic nuclei powered by accreting supermassive black holes can heat the surrounding gas through jets and outflows, preventing cooling flows and regulating star formation. But AGN activity in clusters also depends on environmental factors. In order for a supermassive black hole to become active, it needs a supply of gas that can accrete onto it. In isolated galaxies, this gas may come from the galaxy's own gas reservoir, fed inward by bars, spiral arms, or mergers. In cluster environments, additional mechanisms become possible. Galaxy-galaxy interactions can funnel gas toward galactic centers, triggering AGN activity. Ram pressure from the intracluster medium can compress gas, potentially feeding the central black hole. Conversely, ram pressure stripping can remove the galaxy's gas reservoir, starving the black hole and shutting down AGN activity. Observations of AGN activity in galaxy clusters reveal complex trends. On average, the fraction of galaxies hosting active AGN decreases from the outskirts of clusters toward the centers, suggesting that environmental processes in dense cluster cores somehow suppress AGN activity. However, there is also evidence that AGN activity is enhanced during cluster mergers, when galaxy-galaxy interactions are more frequent and gas is being stirred up by the dynamical disturbances. In MACS J0717, with its ongoing four-way merger, conditions may be particularly favorable for triggering AGN. Some observations support this, showing an elevated fraction of AGN compared to relaxed clusters. However, the relationship between mergers and AGN activity remains debated, with different studies reaching different conclusions depending on the selection criteria and the methods used to identify AGN. The radio jets produced by some AGN in MACS J0717 create visible structures that interact with the surrounding medium. These jets can extend for hundreds of thousands or even millions of light years, far beyond the host galaxy. As the jets propagate, they plow into the ambient gas, creating bow shocks and inflating cavities or bubbles. The relativistic plasma in the jets is less dense than the surrounding thermal gas, so the cavities represent underdense regions that are buoyant and tend to rise through the cluster atmosphere. As they rise, they drag along some of the surrounding gas, creating circulation patterns that distribute energy throughout the cluster. This AGN heating is thought to be the primary mechanism preventing cooling flows in cluster cores, balancing the radiative cooling of the gas and maintaining an equilibrium where gas temperatures remain high despite the short cooling times. The energy budget required for AGN heating is substantial. To offset radiative cooling in a massive cluster, AGN must inject energy at rates of 10 to the 44th ergs per second or more, sustained over billions of years. This corresponds to accreting several solar masses of material onto the central black hole every million years, assuming typical radiative efficiencies. The source of this accreting material is likely the cooling gas itself, creating a self-regulating feedback loop. When the gas cools, it becomes available to accrete onto the black hole, which powers jets that heat the gas, reducing the cooling rate. If heating is too efficient and cooling stops, then the fuel supply for the black hole is shut off, AGN activity declines, and cooling resumes. This negative feedback loop can maintain an approximate balance between heating and cooling over long timescales. The interaction between radio jets and the cluster merger in MACS J0717 creates particularly complex and interesting phenomena. As subclusters merge, the bulk motions of gas can bend or disrupt radio jets, creating unusual morphologies. The enhanced turbulence and bulk motions can also make it difficult for radio jets to establish stable, large-scale structures, leading to more compact or irregular radio sources. Conversely, the jets themselves may affect the merger dynamics by providing additional pressure support or by generating turbulence that affects gas motions. Disentangling these effects requires detailed observations combined with sophisticated simulations that include both the large-scale hydrodynamics of the merger and the small-scale physics of jet propagation and feedback. From a cosmological perspective, the existence of MACS J0717 at redshift 0.548 provides important constraints on structure formation models. The probability of forming a cluster as massive as MACS J0717 by a given redshift depends sensitively on the cosmological parameters, particularly the matter density, the amplitude of initial density fluctuations, and the nature of dark energy. If the universe contains more matter or if the initial fluctuations were larger, then structures form earlier and more massive clusters exist at higher redshifts. If dark energy is stronger, it suppresses structure formation at late times, reducing the number of very massive clusters. By counting the number of clusters with different masses at different redshifts, astronomers can constrain these cosmological parameters. This technique, known as cluster counting or cluster abundance analysis, has become one of the primary methods for measuring cosmological parameters, complementing measurements from the cosmic microwave background, supernova distances, and galaxy clustering. The mass of MACS J0717, 3 quadrillion solar masses, places it among the most massive clusters known at its redshift. The probability of finding such a massive cluster in the observed volume of the universe depends on the cosmological model. Too many such clusters would indicate that the standard cosmological model is incorrect, perhaps requiring modifications to dark energy, dark matter, or even gravity itself. Too few would raise questions about selection effects or observational incompleteness. Current observations suggest that the number of very massive clusters is consistent with the standard lambda-CDM cosmological model, though there are some hints of possible tensions that continue to be investigated. MACS J0717 itself is consistent with being a rare but expected outcome of structure formation in the lambda-CDM framework. The merger of 4 subclusters in MACS J0717 also provides a test of the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. If the universe were fundamentally inhomogeneous, with some regions having systematically different properties than others, then the statistics of structure formation would be different in different regions. The fact that MACS J0717 formed where it did, along a node of the cosmic web where 4 filaments meet, is consistent with the predictions of the cosmological principle combined with random fluctuations. The cosmic web structure itself, with its filaments, walls, and voids, emerges naturally from gravitational instability acting on small initial fluctuations in a homogeneous expanding universe. The location of clusters at web nodes is not a violation of homogeneity, but rather a statistical consequence of how structure grows under gravity. The presence of 4 merging subclusters also tests our understanding of cluster formation timescales. If mergers are too frequent or too rapid, then we would expect to see more systems like MACS J0717 with ongoing multiple mergers. If mergers are rare or slow, such systems would be exceptionally uncommon. The observed frequency of systems like MACS J0717 is roughly consistent with predictions from simulations based on the lambda-CDM model, providing another confirmation that our basic picture of structure formation is correct. However, detailed comparisons between observations and simulations continue to reveal discrepancies and surprises, suggesting that our understanding is not yet complete and that there is still much to learn from systems like MACS J0717. One particularly intriguing question raised by observations of MACS J0717 concerns the ultimate fate of the structure. Over very long timescales, far beyond the current age of the universe, galaxy clusters will evolve in ways that are difficult to predict. Stars will continue to age and die, gradually depleting the population of bright, massive stars and leaving behind fainter, lower-mass stars and stellar remnants like white dwarfs, neutron stars, and black holes. Gas will continue to cool and form new stars, though at ever-decreasing rates as the gas supply is exhausted or expelled. Galaxies will continue to merge, building up a central dominant galaxy that contains an ever larger fraction of the cluster's stellar mass. The cluster itself may merge with neighboring clusters, growing to even larger masses. On timescales of trillions of years, far beyond the current age of the universe of 13.8 billion years, the stars and galaxies will begin to exhaust their nuclear fuel. The most massive stars have already done so, living for only millions of years. Solar mass stars like the Sun will survive for about 10 billion years. The lowest mass red dwarf stars will shine for trillions of years, far longer than the current age of the universe. But eventually, even these long-lived stars will die, and no new stars will form because the gas will have been exhausted or expelled from galaxies. The cluster will enter a degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These remnants will continue to orbit in the gravitational potential of the cluster, occasionally interacting and sometimes being ejected from the cluster entirely through three-body or higher-order dynamical interactions. On even longer timescales, quadrillions or quintillions of years, the stellar remnants themselves will evolve. White dwarfs will gradually cool, becoming black dwarfs that emit no light. Black holes will evaporate through Hawking radiation, a quantum mechanical process that causes black holes to slowly lose mass by emitting particles. The evaporation time for a stellar mass black hole is about 10 to the 67th years, an almost inconceivably long time. Even supermassive black holes will eventually evaporate, though on even longer timescales. The largest black holes, billions of solar masses, will take 10 to the 100 years or more to evaporate. After even these have disappeared, the cluster will consist only of low-mass particles and radiation, dispersed over an enormous volume by the expansion of the universe. This far future is speculative and depends on assumptions about physics that we cannot currently test, but it represents the ultimate endpoint of cosmic evolution if the laws of physics as we currently understand them remain valid. But these far future scenarios lie trillions of years ahead. For now, MACS J0717 is in the prime of its existence, a dynamic and evolving system where massive structures are colliding. Energy is being released at prodigious rates, and the fundamental forces of nature are shaping matter on the largest scales. Studying this system provides a unique opportunity to witness cosmic evolution in action, to test our theories of physics and cosmology, and to appreciate the awesome power and beauty of the universe. Each observation, each new piece of data, adds to our understanding and raises new questions. The story of MACS J0717 is far from complete, and as our instruments improve and our theories develop, we will continue to learn from this remarkable cosmic collision zone for decades to come. The quantum mechanical processes occurring within the plasma of MACS J0717 operate on scales billions of times smaller than the cluster itself, yet they profoundly influence the observable properties of this cosmic giant. When electrons in the hot intracluster medium undergo transitions between energy levels or scatter off ions, they emit photons with specific energies corresponding to the atomic structure of the elements present. These emission lines, visible in X-ray spectra, carry encoded information about temperature, density, velocity, and composition. The width of each spectral line reveals the thermal and turbulent motions of the emitting gas through Doppler broadening. The ratio of different lines from the same element constrains the ionization state and electron density. The presence or absence of particular lines identifies which elements are present and in what abundances. Modern X-ray spectrometers can resolve these features with sufficient precision to extract this information, transforming what appears as a diffuse glow into a detailed census of physical conditions. The ionization balance in the plasma represents an equilibrium between competing processes. Collisional ionization, where fast-moving electrons knock bound electrons off atoms, tends to increase the ionization state. Radiative and dielectronic recombination, where free electrons are captured by ions, tends to decrease it. At the temperatures characteristic of MACS J0717, typically 30 to 100 million degrees, most light elements like carbon, nitrogen, and oxygen are completely stripped of their electrons, existing as bare nuclei. Intermediate mass elements like silicon, sulfur, and argon retain only their innermost electrons. Even iron, with 26 electrons in its neutral state, loses most of them, typically existing in ionization states ranging from iron 17 through iron 25. The exact distribution of ionization states depends on both temperature and density, providing a diagnostic tool for measuring conditions throughout the cluster. Departures from ionization equilibrium can occur in regions where conditions are changing rapidly. Behind a strong shock front, the temperature jumps suddenly, but the ionization state takes time to adjust because recombination and ionization are rate-limited processes that depend on collision frequencies. This creates a non-equilibrium ionization state where the atoms lag behind the temperature, remaining underionized relative to equilibrium expectations. The timescale for reaching equilibrium depends on the density. In denser regions, collisions are more frequent and equilibrium is established quickly, while in lower density regions, the gas can remain out of equilibrium for extended periods. Detecting these non-equilibrium signatures provides direct evidence for recent shocks and allows measurement of shock ages and densities. Some observations of MACS J0717 have found marginal evidence for such effects, though detecting them conclusively requires extremely high-quality spectra with excellent signal-to-noise ratios. The cosmic rays accelerated in MACS J0717 do not remain confined to the cluster indefinitely. While the magnetic fields provide some confinement, the highest energy particles have gyroradii, the radius of their circular orbits around magnetic field lines, that can exceed the scale of the cluster itself. These particles essentially travel in straight lines, barely affected by the magnetic fields, and can escape into intergalactic space. Lower energy cosmic rays are better confined but can still diffuse outward through the cluster over time. This escape of cosmic rays means that galaxy clusters like MACS J0717 act as sources of the intergalactic cosmic ray background, contributing to the population of energetic particles that pervade the universe. The spectrum and composition of escaping cosmic rays carries information about the acceleration mechanisms operating in clusters, and future gamma-ray observatories may be able to detect these escaping particles through their interactions with the cosmic microwave background and extragalactic background light. The inverse Compton process, where relativistic electrons scatter low-energy photons to higher energies, provides another channel for energy loss and radiation in MACS J0717. The cluster is bathed in photons from the cosmic microwave background, the relic radiation from the Big Bang that fills all of space with a nearly uniform bath of photons at a temperature of about 3 degrees Kelvin. Although these photons have very low energy individually, they are extraordinarily numerous, providing an abundant target for inverse Compton scattering. When a relativistic electron moving at nearly the speed of light encounters a cosmic microwave background photon, it can scatter the photon, transferring energy to it and boosting it from microwave wavelengths to X-ray or even gamma-ray wavelengths. This process competes with synchrotron radiation as an energy loss mechanism for relativistic electrons, and in some cases it can be the dominant loss process. The relative importance of inverse Compton versus synchrotron losses depends on the magnetic field strength and the radiation field energy density. In regions with weak magnetic fields, inverse Compton losses dominate. In regions with strong fields, synchrotron losses are more important. By comparing the radio-synchrotron emission with the expected inverse Compton emission in X-rays and gamma rays, astronomers can constrain the magnetic field strength through an independent method that does not rely on equipartition assumptions. Gamma-ray telescopes have searched for inverse Compton emission from MACS J0717 and other massive clusters, with some tentative detections reported but not yet conclusively confirmed. Future gamma-ray observatories with improved sensitivity should be able to detect this emission definitively, opening a new window for studying relativistic particle populations in clusters. The Sunyaev-Zeldovich effect provides yet another way to observe the hot gas in MACS J0717 through its interaction with cosmic microwave background photons. When cosmic microwave background photons pass through the hot intracluster medium, a small fraction of them undergo inverse Compton scattering off the thermal electrons in the gas. This scattering transfers energy from the electrons to the photons, shifting their spectrum in a characteristic way. The net result is a decrease in the intensity of cosmic microwave background radiation at low frequencies and an increase at high frequencies, with the crossover occurring at around 218 GHz. This spectral distortion is wavelength independent in the sense that it depends only on the integrated pressure along the line of sight, not on the redshift of the cluster. This makes the Sunyaev-Zeldovich effect particularly valuable for finding distant clusters, since the signal does not diminish with distance the way optical or X-ray signals do. For MACS J0717, the Sunyaev-Zeldovich effect has been measured by several experiments, including ground-based telescopes and space-based instruments. The measurements confirm the cluster's large mass and reveal the distribution of gas pressure throughout the system. Because the effect depends on pressure rather than density squared like X-ray emission, it is relatively more sensitive to lower density gas in the outskirts of the cluster and in the filaments feeding the cluster. Combined with X-ray observations, Sunyaev-Zeldovich measurements allow astronomers to separate temperature from density, providing tighter constraints on the thermodynamic state of the gas. The Sunyaev-Zeldovich effect also offers the possibility of detecting bulk motions of the gas through the kinetic Sunyaev-Zeldovich effect. A Doppler shift of the spectral distortion caused by the motion of the cluster as a whole or by internal gas flows. Detecting this kinetic effect is challenging but has been accomplished for some clusters, including tentative detections in MACS J0717 that suggest bulk motions consistent with the merger scenario inferred from other observations. The entropy profile of the intracluster medium encodes the history of heating and cooling in the cluster. Entropy, in the thermodynamic sense, is a measure of the disorder or randomness of a system and is related to the temperature and density of the gas. For an ideal gas, the entropy per particle is proportional to the temperature divided by the density to the power of 2/3. In a purely gravitationally heated cluster, where the gas is heated only by the conversion of gravitational potential energy as it falls into the cluster potential well, the entropy should increase outward from the cluster center following a specific power law profile known as the baseline entropy profile. Deviations from this baseline indicate additional heating or cooling processes. In the cores of clusters, entropy is often lower than the baseline prediction, indicating that radiative cooling has removed energy from the gas. In the outskirts, entropy can be higher than baseline, suggesting preheating by feedback processes before the gas fell into the cluster, or heating by shocks during the cluster's formation. In merging clusters like MACS J0717, the entropy distribution becomes highly complex and irregular. Shock waves add entropy to the gas they pass through, creating high-entropy regions downstream of shocks. Adiabatic compression behind shocks increases pressure and temperature but leaves entropy relatively unchanged. Mixing of gas with different temperatures and densities creates intermediate entropy values. By mapping the entropy distribution using combined X-ray and Sunyaev-Zeldovich observations, astronomers can reconstruct the heating history of the gas and identify which regions have been shocked, which have been adiabatically compressed, and which retain relatively undisturbed gas from before the merger. The clumpiness of the gas distribution in MACS J0717 affects how we interpret observations and introduces systematic uncertainties in mass measurements. X-ray emission depends on the square of the gas density, so clumpy gas with density fluctuations emits more X-rays than smooth gas with the same average density. If we assume the gas is smooth when it is actually clumpy, we will overestimate the average density and consequently overestimate the mass. This clumping bias can be as large as 20 to 30% in merging clusters where turbulence and shocks create significant density fluctuations. Correcting for clumping requires understanding the statistical properties of the fluctuations, which can be constrained through detailed analysis of surface brightness variations in X-ray images or through comparisons between X-ray and Sunyaev-Zeldovich observations, which have different dependencies on density. The three-dimensional structure of MACS J0717 is partially obscured by projection effects, since we observe the cluster in projection on the sky and cannot directly measure distances along the line of sight. A structure that appears elongated in the plane of the sky might be intrinsically elongated or might simply be extended along our line of sight. Determining the true three-dimensional geometry requires additional information, such as spectroscopic measurements of galaxy velocities to determine positions along the line of sight through Hubble's law, or careful analysis of the X-ray and lensing data to constrain the mass distribution in 3 dimensions. Numerical simulations of clusters show that mergers often occur along preferred directions related to the large-scale filamentary structure of the cosmic web, with subclusters typically falling in long filaments. For MACS J0717, the elongated structure visible in observations, aligned with the directions of the infalling subclusters, strongly suggests that the merger is occurring preferentially in the plane of the sky, though there are certainly also components of motion along the line of sight. The role of baryons in structure formation extends beyond simply tracing the dark matter distribution. While dark matter dominates the mass and determines the overall gravitational potential, baryonic processes introduce physics that dark matter does not experience. Gas can radiate energy, cooling and forming stars. Stars inject energy back into the gas through stellar winds and supernovae. Supermassive black holes generate powerful outflows that can expel gas from galaxies and clusters. These baryonic processes, collectively known as feedback, can significantly modify the distribution of matter within dark matter halos, creating cores in what would otherwise be cuspy dark matter profiles, reducing the baryon fraction in low-mass halos, and affecting the sizes and concentrations of galaxies and clusters. In massive clusters like MACS J0717, the efficiency of feedback is reduced because the gravitational potential is so deep that it is difficult to expel gas completely. Nevertheless, feedback still matters, particularly in regulating star formation in the galaxies and in preventing excessive cooling in cluster cores. The balance between gravitational heating, radiative cooling, and feedback heating determines the final state of the gas and the properties of the galaxy population. Understanding this balance quantitatively requires combining observations with sophisticated simulations that include the relevant physical processes, from galaxy-scale star formation and black hole accretion to cluster-scale hydrodynamics and gravitational dynamics. Simulations of MACS J0717 face significant computational challenges due to the range of scales that must be resolved. The cluster itself is about 15 million light-years across, but to accurately model processes like star formation and feedback requires resolving structures down to parsec scales or smaller, a factor of more than 10 million in spatial scale. Including all these scales in a single simulation is computationally prohibitive with current technology. Instead, astronomers use different strategies. Some simulations focus on the large-scale dynamics and treat small-scale processes like star formation and feedback using simplified subgrid models, mathematical prescriptions that capture the average effects without explicitly resolving the detailed physics. Other simulations zoom in on smaller regions and resolve the small-scale physics in detail but sacrifice the large-scale context. Ideally, both approaches are combined, using large-scale simulations to provide boundary conditions and context for high-resolution zooms, and using the high-resolution results to calibrate the subgrid models used in large-scale simulations. The comparison between simulations and observations is not straightforward. Observations provide surface brightness distributions, spectra, and morphologies, but simulations output particle positions, velocities, and thermodynamic properties. Converting simulation outputs into observable quantities requires forward modeling, where the simulation results are processed through synthetic observing pipelines that account for instrument response, projection effects, and observational noise. Only after this forward modeling can simulation predictions be directly compared to observations. This process has become increasingly sophisticated, with mock observations from simulations now routinely including realistic noise, point spread functions, detector responses, and even selection effects. The comparison reveals that simulations generally reproduce the overall properties of clusters like MACS J0717 reasonably well but often struggle with detailed predictions, particularly regarding the properties of the galaxy population, the level of turbulence, and the structure of shocks and cold fronts. One persistent discrepancy concerns the concentration of dark matter halos. Simulations generally predict that halos should be more concentrated than observations suggest, with steeper density profiles in the inner regions. This concentration problem is related to the missing satellites problem and the core cusp problem, forming a trio of small-scale challenges to the cold dark matter paradigm. Various solutions have been proposed, including warm dark matter, self-interacting dark matter, and baryonic feedback that redistributes dark matter through gravitational interactions. For galaxy clusters, baryonic feedback is less effective at modifying the dark matter distribution than it is for galaxies, so the concentration problem might point toward dark matter physics rather than baryonic effects. However, the observational constraints remain somewhat uncertain, and it is possible that improved observations and better analysis methods will resolve the apparent discrepancy within the standard cold dark matter framework. The study of MACS J0717 contributes to the broader effort to understand the cosmic baryon cycle, the circulation of baryonic matter between different phases and locations. Baryons originate in the Big Bang as primordial hydrogen and helium. They then cool and condense into the first stars and galaxies, where nuclear fusion creates heavy elements. Supernova explosions and stellar winds eject these heavy elements back into the interstellar medium, enriching the gas. Galactic winds driven by supernovae and active galactic nuclei can expel enriched gas from galaxies into the intergalactic medium, or into the halos surrounding galaxies. Gas in halos can cool and accrete back onto galaxies, fueling new star formation. In galaxy clusters, ram pressure stripping removes gas from galaxies and adds it to the intracluster medium. The hot intracluster medium itself can cool and form stars in the central galaxy or be heated by active galactic nuclei, preventing cooling. This complex cycle operates over cosmic time, with different processes dominating at different epochs and in different environments. In the early universe, gas accretion onto galaxies was rapid and star formation rates were high. As the universe evolved and grew less dense, accretion slowed and feedback became more effective at regulating star formation. In dense environments like galaxy clusters, environmental quenching processes shut down star formation in many galaxies, transforming star-forming spiral galaxies into quiescent elliptical galaxies. Tracking the baryon budget, accounting for where all the baryons are at different times, is essential for understanding galaxy evolution and for reconciling observations with cosmological predictions of the total baryon abundance. MACS J0717, with its large mass and ongoing merger, serves as a laboratory for studying many aspects of the baryon cycle simultaneously, from star formation and quenching in galaxies to heating and mixing in the intracluster medium. The observational selection effects that led to the discovery and study of MACS J0717 also influence our interpretation of the cluster. MACS J0717 was discovered as part of the Massive Cluster Survey, a program specifically designed to find the most massive clusters at intermediate to high redshifts. The survey used archival X-ray data to identify bright, extended X-ray sources indicative of hot intracluster gas. This selection naturally biases toward massive, X-ray luminous clusters, which tend to be dynamically active systems with ongoing mergers that enhance X-ray emission through shock heating. Relaxed clusters with smooth X-ray profiles may be systematically underrepresented in such surveys. Understanding and correcting for these selection effects is crucial when using cluster samples to constrain cosmology, since the statistics of cluster abundance are sensitive to selection. If we do not account for the fact that our sample is biased toward merging clusters, we might draw incorrect conclusions about the true abundance of massive clusters and hence about cosmological parameters. Follow-up studies of MACS J0717 using various telescopes have been extensive, motivated by the cluster's extreme properties and its utility as a gravitational lens. Deep imaging with the Hubble Space Telescope has mapped the strong lensing features and provided photometry for thousands of galaxies. Spectroscopy with ground-based telescopes has measured redshifts for hundreds of cluster members and lensed background galaxies. Long exposures with the Chandra X-ray Observatory have revealed detailed temperature and density structures. Radio observations with the Very Large Array and other facilities have mapped the diffuse synchrotron emission and identified individual radio sources. Infrared observations with Spitzer and Herschel have detected dust-obscured star formation in cluster galaxies. Millimeter-wave observations have measured the Sunyaev-Zeldovich effect. This multi-wavelength dataset, accumulated over more than a decade of observations, makes MACS J0717 one of the most comprehensively studied galaxy clusters in existence. Despite this wealth of data, many questions about MACS J0717 remain unanswered. The precise masses and trajectories of the four merging subclusters are still uncertain, with different studies reaching somewhat different conclusions depending on which observational constraints they prioritize. The merger is likely complex, with subclusters in different phases of merging, some approaching for the first time, others perhaps on second or third passages. Disentangling this complexity requires combining all available data with sophisticated simulations, a task that remains challenging. The origin of the diffuse radio emission is debated, with questions about whether it is produced primarily by shock acceleration, turbulent reacceleration, or a combination of processes. The role of magnetic fields in confining cold gas structures and suppressing thermal conduction remains poorly constrained. The history of star formation and chemical enrichment in the cluster galaxies is incompletely understood. Each of these questions motivates ongoing research and future observations. The future of MACS J0717 studies will benefit from upcoming observatories and instruments. The James Webb Space Telescope is already providing infrared observations of unprecedented depth and resolution, revealing dust-obscured star formation and allowing detailed studies of the lensed high-redshift galaxies. The next generation of X-ray observatories, including missions in development that would provide high-resolution spectroscopy and large collecting area, will enable detailed mapping of gas velocities, turbulence, and non-equilibrium ionization throughout the cluster. Extremely large telescopes on the ground will provide optical and infrared spectroscopy with resolution and sensitivity far exceeding current capabilities, allowing measurements of galaxy kinematics, chemical abundances, and star formation histories for hundreds of cluster members. The square-kilometer array, once completed, will revolutionize radio observations of clusters, detecting faint diffuse emission and resolving structures on scales from parsecs to megaparsecs. Theoretical developments will also advance our understanding. More realistic simulations that include additional physics, such as cosmic rays, magnetic fields, thermal conduction, and viscosity, are being developed and run. Machine learning techniques are being applied to analyze the complex multidimensional datasets produced by observations and simulations, identifying patterns and correlations that traditional analysis methods might miss. New analytical models are being developed to understand the nonlinear processes occurring in cluster mergers, providing insights that complement numerical simulations. The synergy between advancing observations, improving simulations, and developing theory promises continued progress in understanding systems like MACS J0717. The philosophical implications of studying MACS J0717 extend beyond astrophysics. This cluster, with its violence and grandeur, reminds us of the immense scales and energies present in nature, scales that dwarf human experience and challenge human comprehension. The fact that we can study such a system at all, that we can detect light that has traveled for over 5 billion years, decode its information, and reconstruct the physical conditions in a region of space we will never directly visit, demonstrates the power of science and human intellect. We are able to extend our understanding far beyond our immediate surroundings, grasping the workings of the universe through observation, reason, and mathematics. This ability is one of humanity's greatest achievements. At the same time, studying MACS J0717 reveals the limits of our knowledge. We observe dark matter only through its gravitational effects, unable to detect it directly or understand its fundamental nature. We infer the presence of dark energy from cosmic acceleration, but have no compelling theory explaining what it is. We see structures in the cluster that simulations struggle to reproduce, hinting at gaps in our understanding of the relevant physics. We make measurements with uncertainties, sometimes finding discrepancies between different observational methods that suggest systematic errors we do not fully understand. Science is a process of constant refinement, where each answer raises new questions and where certainty is always provisional, subject to revision in light of new evidence. The collaborative nature of modern astronomy is exemplified by the study of MACS J0717. No single astronomer, or even single research group possesses all the expertise needed to fully analyze this system. X-ray astronomers, optical astronomers, radio astronomers, theorists, and observers must all contribute their specialized knowledge. Data from multiple telescopes, operated by different agencies and countries, must be combined. Papers presenting results from MACS J0717 often have dozens of co-authors representing institutions across the globe. This international collaboration reflects the universal nature of science, transcending national boundaries and political divisions in pursuit of shared understanding. The knowledge gained from studying MACS J0717 belongs to all humanity, not to any single nation or group. Educational and outreach efforts bring the science of MACS J0717 to broader audiences. Images of the cluster, with its colorful overlays showing X-ray gas, dark matter distributions, and optical galaxies, appear in museums, planetariums, and online. Simplified explanations appear in popular science articles and books. Educators use the cluster as an example when teaching about gravity, dark matter, or cosmology. Through these efforts, the discoveries made by professional astronomers studying MACS J0717 become part of human culture and collective knowledge, inspiring wonder and curiosity in people of all ages and backgrounds. The naming of astronomical objects follows conventions established by astronomical unions and survey teams. MACS J0717 derives its name from the Massive Cluster Survey, abbreviated MACS, followed by coordinates indicating its position on the sky. The J indicates that the coordinates are in the J2000 coordinate system, and 0717 is a truncated version of the right ascension, 7 hours 17 minutes. The full designation includes additional digits specifying the declination. While this systematic naming scheme lacks the poetry of mythological constellation names or the personal recognition of objects named after their discoverers, it provides an efficient way to catalog the hundreds of thousands of astronomical objects now known. Still, astronomers often develop informal nicknames for objects they study extensively, and MACS J0717 is sometimes called simply MACS 717 in casual conversation among researchers. The archive of observations of MACS J0717 represents a valuable scientific resource that will continue to yield discoveries for years to come. As analysis techniques improve and new theoretical insights emerge, astronomers can reanalyze archival data and extract information that was not initially recognized. Data that seemed marginally significant when first obtained might become highly significant when combined with new observations or when analyzed with improved methods. The practice of archiving astronomical data and making it publicly available ensures that investments in telescope time continue to pay scientific dividends long after the original observations were made. MACS J0717 exemplifies this, with early X-ray observations from the 1990s and early 2000s still being used in recent papers alongside the latest data from current missions. The thermodynamic evolution of gas parcels traversing MACS J0717 follows trajectories through phase space that encode the complete history of their interactions. Each parcel of gas begins its journey in the cosmic web filaments, gradually flowing toward the cluster along trajectories determined by the large-scale gravitational field. During this infall phase, the gas undergoes gentle heating as gravitational potential energy converts to kinetic energy. The infalling gas remains relatively cool, perhaps only a few 100,000 to a million degrees, and maintains fairly low density. Upon entering the virial radius of the cluster, typically defined as the radius within which the average density is about 200 times the critical density of the universe, the gas begins experiencing stronger tidal forces and increased pressure from the cluster's existing atmosphere. The moment of shock crossing represents a catastrophic transition for an infalling gas parcel. Within a distance comparable to a mean free path, typically only a few light-years in the tenuous outer regions, the gas velocity drops precipitously from thousands of kilometers per second to near zero in the cluster rest frame. Simultaneously, the temperature spikes upward by factors of 10 or more, reaching tens of millions of degrees. The density increases by factors of 4 or more depending on the shock strength. This violent transition converts the ordered kinetic energy of bulk motion into the random thermal motions of particles. From the perspective of individual particles, the shock is not experienced as a discrete event but rather as a statistical shift in the velocity distribution. particles repeatedly scatter off magnetic irregularities and other particles, gradually decelerating and randomizing their velocities over many collision timescales. The post-shock gas does not remain static but continues evolving through a sequence of hydrodynamic instabilities and mixing processes. The freshly shocked gas is often not in pressure equilibrium with its surroundings, leading to expansion or compression until equilibrium is achieved. Contact discontinuities, boundaries between gas regions with different temperatures or densities but the same pressure, develop and can become sites of Kelvin-Helmholtz instabilities. These instabilities grow from small perturbations at the interface, developing into rolling vortices that mix the two gas phases together. The mixing timescale depends on the velocity difference across the interface and the presence of magnetic fields, which can partially stabilize the instability. Observations of MACS J0717 show features suggestive of Kelvin-Helmholtz instabilities at several locations, including spiral patterns and finger-like protrusions along the edges of cool cores being stripped from infalling subclusters. Rayleigh-Taylor instabilities develop when denser gas is supported against gravity by less dense gas below it, creating an unstable configuration analogous to trying to float lead on water. In MACS J0717, such configurations arise when dense cool cores are ram pressure stripped and pushed upward through less dense hot gas. The instability causes the dense gas to develop finger-like protrusions that sink downward while the less dense gas rises as bubbles. These rising bubbles and sinking fingers increase the surface area between the two phases, accelerating mixing. The growth rate of Rayleigh-Taylor instabilities depends on the density contrast and the effective gravity, which in cluster environments includes both gravitational acceleration and ram pressure forces. Magnetic fields threading through the interface can again provide stabilization, particularly if the field lines are oriented perpendicular to the direction of the instability growth. The role of viscosity in the intracluster medium has been debated extensively. A fully ionized plasma has both collisional viscosity arising from particle collisions and potentially effective viscosity arising from magnetic field effects. The collisional viscosity is quite low in cluster conditions, with viscous timescales far exceeding the age of the universe for typical cluster parameters. This suggests that the plasma should behave essentially as an inviscid fluid for most purposes. However, at very small scales, particularly near steep gradients, viscosity might become important. Additionally, some theories propose that plasma instabilities could generate effective turbulent viscosity at larger scales, though this remains uncertain. The near-inviscid nature of the intracluster medium has important implications for phenomena like cold fronts, allowing them to remain sharp rather than being smeared out by viscous diffusion. Thermal conduction in magnetized plasma presents fascinating physics relevant to MACS J0717. In an unmagnetized plasma, electrons can freely travel and conduct heat efficiently, with thermal conductivity depending on temperature to the 5/2 power. This high conductivity would rapidly erase temperature gradients, conducting heat from hot regions to cool regions on timescales of only millions of years. However, magnetic fields dramatically suppress conduction perpendicular to field lines while leaving parallel conduction relatively unaffected. Electrons spiral around magnetic field lines with small gyroradii and are effectively confined to move only along field lines. If field lines are tangled and randomly oriented, heat must diffuse along a tortuous path, greatly increasing the effective conduction timescale. The suppression factor depends on the tangling scale and the field geometry, with typical estimates suggesting that effective conduction is reduced by factors of tens to hundreds compared to the classical unmagnetized value. The survival of temperature discontinuities at cold fronts in MACS J0717 provides observational evidence for suppressed thermal conduction. These cold fronts maintain sharp temperature jumps over hundreds of millions of years, far longer than classical conduction would permit. The magnetic field orientation at cold fronts has been studied using X-ray polarimetry and through inference from the sharpness of the front itself. Results suggest that field lines tend to be draped along the cold front interface, lying parallel to the discontinuity. This geometry maximizes the path length for perpendicular conduction, providing optimal suppression of heat flow. Additionally, plasma instabilities such as the magnetothermal instability may develop at cold fronts, generating magnetic field turbulence that further inhibits conduction. Resonant scattering of X-ray line photons introduces another microphysical process affecting the observable properties of MACS J0717. When a photon is emitted at an energy corresponding to an atomic transition, it can be absorbed by another ion of the same species in the same ionization state, which then re-emits another photon in a random direction. This scattering process can cause photons to diffuse spatially before escaping the cluster, potentially smoothing out small-scale brightness variations and introducing polarization if the emission region has temperature or velocity gradients. Resonant scattering is most effective for strong transitions and in regions with high optical depth, conditions that can be met in the cool cores of clusters. For MACS J0717, the disturbed nature of the system and the high temperatures reduce the importance of resonant scattering compared to more relaxed, cool core clusters, but it may still affect the interpretation of emission lines from the coolest regions. The escape of photons from MACS J0717 involves propagating through an expanding universe, undergoing cosmological redshift that shifts their wavelengths to longer values. A photon emitted at X-ray energies of several keV from MACS J0717 arrives at Earth with energy reduced by a factor of approximately 1.55 due to the redshift. This energy loss must be accounted for when comparing observed spectra to theoretical models of the emitting plasma. The redshift also affects the inferred luminosity of the cluster. For a given observed flux, higher redshift objects are more luminous intrinsically due to their greater distance, and because their emission is compressed in time due to cosmological time dilation. This time dilation factor of 1 plus c means that variability timescales appear lengthened, though for slowly evolving systems like galaxy clusters, this effect is usually negligible compared to other uncertainties. Weak gravitational lensing by MACS J0717 extends far beyond the regions of strong lensing where multiple images and arcs form. Throughout a much larger area surrounding the cluster, extending to several virial radii, the gravitational field produces subtle distortions in the shapes of background galaxies. Each background galaxy is slightly stretched tangentially with respect to the cluster center, by typically only a few percent. This tiny signal is undetectable in any individual galaxy but emerges statistically when averaging over hundreds or thousands of background galaxies. The tangential alignment signal directly measures the projected mass distribution of the cluster without relying on assumptions about dynamical state or hydrostatic equilibrium. Weak lensing therefore provides crucial independent mass estimates that can be compared to masses inferred from X-ray observations, galaxy kinematics, or the Sunyaev-Zeldovich effect. Systematic uncertainties in weak lensing analysis arise from several sources. The intrinsic shapes of galaxies are not perfectly known and must be statistically characterized. Galaxies have some intrinsic tendency to align with the large-scale structure of the universe, a phenomenon called intrinsic alignment, which can mimic or suppress the lensing signal. The point spread function of the telescope, which blurs images and distorts shapes, must be accurately characterized and deconvolved. Photometric redshift estimates for background galaxies have uncertainties that propagate into the lensing analysis since the lensing efficiency depends on the distance ratio between lens and source. Despite these challenges, weak lensing has matured into a precise technique, and for well-studied systems like MACS J0717, weak lensing masses typically agree with other mass estimates to within 20% or better. The distribution of galaxies within MACS J0717 traces the assembly history through their spatial and velocity distributions. Red elliptical galaxies, which have ceased forming stars and have old stellar populations, tend to concentrate toward the cluster center, while blue star-forming galaxies are more common in the outskirts. This morphology-density relation has been observed in essentially all galaxy clusters and reflects the environmental processes that quench star formation. Galaxies that fell into the cluster long ago have had time to be processed by ram pressure stripping, harassment, and other mechanisms, transforming them into red, quiescent systems. Galaxies currently falling in retain their star-forming character until environmental effects shut down their star formation. The velocity distribution of cluster galaxies shows multiple peaks corresponding to the different subclusters, providing direct evidence for the ongoing merger. Spectroscopic surveys have measured redshifts for hundreds of galaxies in the MACS J0717 region, revealing distinct velocity components separated by thousands of kilometers per second. The velocity dispersions within each subcluster, typically around 1,000 kilometers per second, reflect the gravitational potential depth of each component. These velocity measurements combined with position information allow astronomers to assign galaxies to specific subclusters and to estimate the relative velocities of the merging components. However, projection effects complicate the analysis. The observed line-of-sight velocities represent only one component of the three-dimensional velocity vectors, and velocities perpendicular to the line of sight remain unmeasured. Phase space analysis, plotting galaxy positions versus velocities, provides additional insights into the merger dynamics. Galaxies that recently fell into the cluster from the field occupy a specific region of phase space characterized by large radii and large velocities relative to the cluster mean. As galaxies orbit within the cluster potential, they gradually lose energy through dynamical friction and move to smaller radii and lower velocities. Long-time cluster members occupy the central regions of phase space, near the cluster center with velocities close to the cluster mean. By examining the phase space distribution of galaxies in MACS J0717, astronomers can estimate the infall rate, identify recently accreted galaxies, and constrain the mass accretion history. Comparisons with simulations allow quantitative estimates of these properties, though degeneracies between different evolutionary scenarios remain. The luminosity function of galaxies in MACS J0717, which describes the number of galaxies as a function of brightness, differs from that of the field due to environmental effects. Clusters typically show an excess of bright elliptical galaxies compared to the field, particularly the brightest cluster galaxy, which often sits at the cluster center and has grown through mergers and accretion. Conversely, clusters may show a deficit of faint blue galaxies if these have been accreted and quenched. The exact shape of the cluster luminosity function depends on the cluster's mass and evolutionary state. For MACS J0717, the ongoing merger complicates the interpretation since multiple subclusters each have their own bright central galaxies, and it is unclear which will ultimately become the single brightest cluster galaxy of the merged system. The star formation history of cluster galaxies can be reconstructed through spectroscopic analysis of stellar absorption features and through multi-wavelength photometry that constrains the ages and metallicities of stellar populations. Older stars produce light dominated by red and near-infrared wavelengths, while younger stars shine brightly in blue and ultraviolet. By measuring the spectral energy distribution across many wavelengths and fitting stellar population models, astronomers can determine when most of the stars in each galaxy formed. For MACS J0717 galaxies, these analyses reveal predominantly old stellar populations in red elliptical galaxies, with formation times typically more than 8 billion years ago, well before the galaxies fell into the cluster. Star-forming blue galaxies show ongoing star formation but also contain older stellar populations formed earlier in their histories. The satellite populations around massive cluster galaxies offer additional probes of assembly history. Each massive galaxy is surrounded by a swarm of smaller satellite galaxies gravitationally bound to it. The number, spatial distribution, and properties of satellites depend on the assembly history of the host galaxy and on environmental effects. In the field, satellites remain relatively undisturbed, but in clusters, tidal forces from the cluster potential and high-speed encounters with other galaxies can strip stars from satellites or completely disrupt them. The diffuse intracluster light observed in MACS J0717 likely originates partly from disrupted satellites. By counting satellites around cluster galaxies and comparing to predictions from simulations, astronomers can test models of galaxy formation and environmental processing. Globular clusters, dense spherical collections of stars orbiting within galaxies, provide another tracer of galaxy assembly. Each galaxy hosts a population of globular clusters, with more massive galaxies hosting more clusters. Globular clusters are ancient, typically 10 to 13 billion years old, and their properties encode information about conditions during galaxy formation. The color distribution of globular clusters often shows bimodality, with peaks corresponding to metal-poor and metal-rich subpopulations. This bimodality is thought to reflect two formation epochs: metal-poor clusters forming in the early universe from primordial gas, and metal-rich clusters forming later during major mergers or starbursts. Some galaxies in MACS J0717 have been studied at sufficient resolution to detect their globular cluster populations, revealing thousands of clusters per massive galaxy consistent with expectations. Planetary nebulae, the glowing shells of gas ejected by dying sun-like stars, serve as tracers of stellar populations in cluster galaxies despite their faintness. These objects emit strongly in specific narrow emission lines, allowing them to be detected through narrowband imaging that filters out continuum light. By counting planetary nebulae in cluster galaxies and in the intracluster light, astronomers can trace the distribution of intermediate-age stellar populations, since planetary nebulae have lifetimes of only tens of thousands of years and indicate where stars have recently died. This technique has been applied to some clusters similar to MACS J0717, revealing that the intracluster light contains planetary nebulae and therefore must contain substantial populations of intermediate-age stars liberated from galaxies relatively recently. The chemical abundance patterns in cluster galaxies reveal nucleosynthetic histories shaped by generations of stars. Elements lighter than iron are produced primarily through charged particle fusion in stellar cores and supernova explosions, with different elements produced by different processes and stellar masses. Alpha elements like oxygen, neon, magnesium, silicon, and sulfur are produced copiously in massive stars that explode as Type II supernovae within tens of millions of years of formation. Iron peak elements are produced both in Type II supernovae and in Type I supernovae, which occur when white dwarfs and binary systems accrete matter and explode, with delays of hundreds of millions to billions of years after star formation. The ratio of alpha elements to iron therefore indicates the timescale of chemical enrichment. High alpha to iron ratios indicate rapid enrichment dominated by massive stars, while lower ratios indicate longer timescales where Type I supernovae contribute significantly. Measurements of abundance patterns in MACS J0717 galaxies reveal mostly solar or slightly supersolar alpha to iron ratios in massive elliptical galaxies, indicating that these galaxies formed their stars rapidly at early times and then became quiescent before Type I supernovae could substantially alter the abundance patterns. Spiral galaxies show lower alpha to iron ratios consistent with more extended star formation histories. The intracluster medium shows abundance patterns intermediate between the extreme alpha enhancement of massive ellipticals and solar ratios, reflecting contributions from both core collapse and Type I supernovae integrated over the histories of all the galaxies that have contributed gas to the intracluster medium. Neutron capture elements, including elements heavier than iron, provide additional nucleosynthetic constraints. These elements are produced primarily through the rapid neutron capture process, or R process, which occurs in neutron-rich environments such as neutron star mergers and certain types of supernovae. The S process, or slow neutron capture, occurs in asymptotic giant branch stars. Measurements of these heavy elements remain challenging even in nearby clusters due to the weakness of their spectral signatures, but future extremely large telescopes may enable such measurements in MACS J0717 galaxies, providing unique insights into the rates of rare nucleosynthetic events. The cosmic ray population in MACS J0717 includes not just relativistic electrons responsible for synchrotron emission, but also protons and heavier nuclei. These hadronic cosmic rays do not radiate synchrotron emission efficiently but interact with the thermal gas and with photon fields through different processes. Proton-proton collisions produce pions, which decay into gamma rays, neutrinos, and secondary electrons and positrons. These secondary electrons contribute to the radio emission and X-ray emission through synchrotron radiation and inverse Compton scattering. The gamma rays produced in pion decays have characteristic energies and spectra that differ from those produced by inverse Compton scattering of primary electrons, allowing the two processes to be distinguished observationally in principle, though in practice the distinction requires high-quality gamma-ray spectra that are currently at the limit of detectability. Neutrinos produced by cosmic ray interactions pass through the cluster unimpeded and propagate across the universe, potentially detectable by neutrino telescopes on Earth if the flux is sufficiently high. Detecting neutrinos from MACS J0717 would provide direct evidence for hadronic cosmic ray acceleration and would constrain the cosmic ray energy density independent of electromagnetic observations. Current neutrino telescopes have searched for signals from galaxy clusters without definitive detections, but next-generation instruments, with larger effective areas and better angular resolution, may succeed. The detection of a single high-energy neutrino from a known cluster would be scientifically valuable, though distinguishing cluster neutrinos from the atmospheric and astrophysical background remains challenging. The magnetic field strength in MACS J0717 can be estimated through several independent methods, each with its own systematic uncertainties and assumptions. Synchrotron emission combined with inverse Compton emission yields one estimate by comparing radio and gamma ray fluxes. Faraday rotation measures provide another estimate by measuring how much the plane of polarization of radio waves rotates as they pass through magnetized plasma. Equipartition arguments, which assume the energy density in magnetic fields equals the energy density in relativistic particles, provide a third estimate. These methods typically agree within factors of a few, giving field strengths of a few microgauss for MACS J0717, comparable to the values found in other massive clusters. The consistency between methods suggests the estimates are reasonably reliable despite the various assumptions involved. The origin of these cluster magnetic fields remains debated. Several mechanisms might contribute. Primordial magnetogenesis during or shortly after the Big Bang could have generated weak seed fields that were subsequently amplified by structure formation. Battery mechanisms in the early universe, such as the Biermann battery where temperature and density gradients generate electric currents and hence magnetic fields, could create seeds. Magnetized outflows from the first stars and galaxies could inject magnetic fields into the intergalactic medium. Turbulent dynamos operating during structure formation could amplify weak seeds by many orders of magnitude. Observations of magnetic fields at high redshifts in the cosmic web and in protoclusters will help distinguish these scenarios, though detecting such weak fields remains technologically challenging. The pressure support provided by cosmic rays and magnetic fields may be dynamically significant in MACS J0717, though quantifying their contribution remains difficult. If the energy density in cosmic rays and fields approaches 10 to 20% of the thermal gas energy density, these non-thermal components could provide significant pressure support, affecting hydrostatic mass estimates derived from X-ray observations. Some theoretical models and simulations suggest cosmic ray pressure becomes increasingly important in cluster outskirts where the gas density is low and cosmic ray confinement may be more effective. Observational constraints on cosmic ray pressure remain indirect, relying on gamma ray upper limits, radio emission modeling, and comparisons between different mass estimation techniques. Future direct measurements of cosmic ray spectra through gamma ray observations will tighten these constraints,